Look up at the night sky on a clear evening, and you'll see thousands of twinkling stars, but what you can't see are the breathtaking cosmic dramas that unfolded long before their light ever reached us. Picture a star, millions of times brighter than our sun, ending its life in a cataclysmic explosion so powerful it outshines entire galaxies. That's the story of a supernova, one of the universe's most violent and awe-inspiring events. But here's the fascinating part. Long after the explosion fades, its remnants linger like ghostly fingerprints, glowing with secrets about how stars live, die, and reshape the cosmos. These radiant remnants are more than just debris. They're cosmic alchemists, forging new elements, sculpting nebulae, and even triggering the birth of new stars. Today, we're diving deep into 46 of these celestial marvels, each with its own unique tale of destruction and rebirth. From the delicate filaments of the Crab Nebula to the vast, shockwave-driven bubbles of Cassiopeia A, we'll uncover how these stellar graveyards reveal the universe's hidden rhythms. So buckle up, we're about to journey through the aftermath of stellar explosions and discover how death in the cosmos fuels the cycle of creation itself. Stars begin their lives in the quiet corners of the universe, cradled within vast, swirling clouds of gas and dust called nebulae. Over millions of years, gravity pulls these particles together, heating them until nuclear fusion ignites, a process that turns hydrogen into helium, lighting up the newborn star like a cosmic furnace. For much of its life, a star exists in a delicate balance, with the outward pressure of fusion countering the inward crush of gravity. But just like a candle burning down, every star eventually runs out of fuel. For smaller stars like our Sun, the end is relatively gentle. They expand into red giants before shedding their outer layers, leaving behind a cooling ember known as a white dwarf. But for stars many times more massive, death comes with a far more spectacular finale. When their cores can no longer sustain fusion, gravity wins in a sudden, catastrophic collapse. The star's outer layers slam inward before rebounding in a shockwave so powerful it rips the star apart in a supernova explosion. In that single, blinding moment, a supernova can outshine entire galaxies, releasing more energy than our Sun will produce in its entire lifetime. The explosion flings heavy elements like carbon, oxygen, and even gold far into space, enriching the cosmos with the building blocks of planets and life. But the story doesn't end there. What remains after the fireball fades are the radiant remnants, expanding clouds of gas and dust, neutron stars, or even black holes, each a breathtaking testament to the star's violent demise. These remnants don't just mark an ending, they're the beginning of new cosmic possibilities. Supernova remnants are like cosmic crime scenes, where a star's violent end leaves behind clues for scientists to piece together. These expanding clouds of gas and dust aren't just debris, they're dynamic, evolving structures that glow across the electromagnetic spectrum. Picture ripples in a pond after a stone drops, but on an unimaginable scale. The shockwaves from the explosion plow through space at thousands of kilometers per second, heating interstellar material and lighting it up in vivid X-rays and radio waves. What makes these remnants so fascinating is their diversity. Take the Crab Nebula, for example, a tangled web of glowing filaments powered by a spinning neutron star at its heart, lashing the surrounding gas with intense radiation. Then there's the Veil Nebula, a delicate lacework of ionized gas stretching over dozens of light years, revealing where the shockwave collided with colder interstellar material. Each remnant has its own unique fingerprint, shaped by the star's original mass, the energy of the explosion, and even the environment it blasted into. But these cosmic fossils aren't just beautiful, they're also vital laboratories. Inside their turbulent hearts, particles are accelerated to near light speed, creating cosmic rays that bombard our planet daily. The extreme conditions even forge heavy elements like iron and gold, scattering them across the galaxy to one day become part of new stars, planets, or even life. Supernova remnants are proof that destruction and creation are two sides of the same cosmic coin, and with advanced telescopes, we're now uncovering hidden gems like Cassiopeia A's brilliant shock fronts, or the faint, ancient echoes of explosions that happened millennia before telescopes existed. Every one holds a piece of the puzzle, helping us decode the life cycles of stars and the evolution of the universe itself. Among supernova remnants, few are as iconic or as well studied as the Crab Nebula, a swirling tapestry of gas and dust that's been mesmerizing astronomers for nearly 1,000 years. This cosmic masterpiece was born from a supernova so bright it was recorded by Chinese and Arabic astronomers in the year 1054, visible even in broad daylight for weeks. Today, what remains is a rapidly expanding cloud of filaments, glowing in vibrant hues as they're bombarded by radiation from the nebula's beating heart, a pulsar spinning 30 times per second, lashing its surroundings with powerful magnetic fields and particle jets. What makes the Crab Nebula truly special isn't just its beauty, it's the way it serves as a cosmic laboratory. The pulsar's relentless energy accelerates electrons to nearly the speed of light, causing the entire nebula to shine across the electromagnetic spectrum, from radio waves to gamma rays. This makes it one of the few remnants where we can study the intimate connection between a neutron star and the debris of its progenitor star. Even the nebula's expansion rate, about 1,500 kilometers per second, gives us a front-row seat to how shockwaves sculpt interstellar material over centuries. But the Crab Nebula isn't just a relic of the past, it's a dynamic, evolving system. The pulsar's wind collides with older ejected material, creating intricate structures that resemble ripples in a pond. Some filaments are rich in helium and carbon, remnants of the star's final nuclear reactions, while others bear traces of heavier elements forged in the explosion itself. It's a vivid reminder that even in destruction, stars seed the universe with the ingredients for new beginnings, and because the crab's light has traveled for nearly 1,000 years to reach us, we're not just observing a distant object, we're peering back in time, watching the aftermath of a stellar cataclysm that shaped our understanding of the cosmos. This nebula is more than a celestial landmark. It's a bridge between ancient astronomy and modern astrophysics, challenging us to unravel how neutron stars power their surroundings and what that means for the broader life cycle of galaxies. Yet as stunning as the Crab Nebula is, it's just one of countless stellar remnants, each with its own secrets waiting to be uncovered. Take Cassiopeia A, for example, another breathtaking remnant with a story just as dramatic, but written in an entirely different cosmic language. While the Crab Nebula offers us a window into star death from nearly a millennium ago, Cassiopeia A is practically a newborn by cosmic standards, its light first reaching Earth just over 300 years ago. Imagine if astronomers in the late 17th century had powerful telescopes. They might have witnessed one of the most brilliant stellar explosions in our galactic neighborhood. Instead, we're left with its aftermath, a tangled, high-energy wreckage field that's become a treasure trove for scientists. What makes Cassiopeia A so captivating is its raw, unfiltered violence. Unlike the Crab Nebula with its orderly pulsar, Cas A's heart remains enigmatic. No clear neutron star pulses at its center, suggesting the explosion might have left behind something even stranger, like a quiet black hole or a mangled stellar corpse. But the real spectacle lies in its shockwaves. Filaments of oxygen, silicon, and iron blaze across the remnant, twisted into bizarre shapes by forces we're still trying to decode. Some regions glow with the heat of 30 million degrees, while others shimmer with neon-like knots of sulfur and argon elements forged in the star's final moments. This chaos isn't random, it's a fossilized record of the star's death throes. The asymmetry of the debris hints that the explosion wasn't a clean, spherical blast, but a lopsided detonation, perhaps triggered by violent convection in the star's core. Even more astonishing are the fast-moving knots, clumps of debris racing outward at 15,000 kilometers per second, some rich with titanium and chromium, metals vital for modern technology. It's as if the star, in its dying act, flung the ingredients of future worlds into the void. Yet Cas A's greatest gift might be how it reshapes our understanding of cosmic chemistry. By mapping its elemental distribution, scientists have found proof that supernovae scatter more than just lightweight elements. They're cosmic forges for the heavier atoms in our phones, jewelry, and even our blood. Every time you inhale oxygen or marvel at a gold ring, you're touching stardust recycled by explosions like this one. And because Cas A is so young, we're watching this recycling process in real time, a rare chance to see how the universe transforms destruction into creation. But as dramatic as Cas A's story is, it's just one chapter in a far larger saga. Beyond it lie remnants that defy even our wildest expectations, some so faint they're barely visible, others glowing with energies we're only beginning to comprehend. Each one whispers a different secret about how stars live, die, and stitch the fabric of the cosmos. In the late autumn of 1572, Danish astronomer Tycho Brahe stepped outside and noticed something impossible: a brilliant new star blazing in the constellation Cassiopeia, shining brighter than Venus. At a time when the heavens were thought to be unchanging, this sudden apparition sparked a revolution in astronomy. Today, we know Tycho wasn't seeing a newborn star, but its spectacular death, a Type Ia supernova whose faint, expanding remnant still glows 4.5 centuries later. What makes Tycho's supernova so pivotal isn't just its historical significance, it's the way this explosion acts as a cosmic yardstick. Unlike the messy collapses of massive stars, Type Ia supernova occur when a white dwarf siphons material from a companion until it crosses a critical threshold, detonating with such predictable brightness that astronomers use them as standard candles to measure the universe's expansion. Tycho's remnant, with its razor-sharp shock fronts and intricate web of silicon-rich debris, is like a frozen snapshot of that instant. The outer edges race outward at 10,000 kilometers per second, while X-ray telescopes reveal clumps of iron and titanium flung asymmetrically, hinting that even these uniform explosions might have chaotic twists. But the real magic of Tycho's remnant lies in what it teaches us about dark energy. By studying how Type Ia supernova dim over time, scientists discovered the universe isn't just expanding, it's accelerating, propelled by some mysterious force. Every observation of Tycho's fading echo helps calibrate those measurements, tightening our grasp on one of cosmology's greatest puzzles. Yet this remnant isn't just a tool, it's a time capsule. Radio telescopes have detected a light echo, faint reflections of the original explosion bouncing off interstellar dust, letting us analyze the 1572 event as if it happened yesterday. And deep within the debris field, Astronomers hunt for the surviving companion star, the white dwarf's accomplice in this cosmic detonation. Finding it would confirm decades of theory about how these stellar time bombs ignite. Tycho's legacy reminds us that the sky isn't static. It's a living theater where cataclysms rewrite the rules, but as groundbreaking as Type Ia supernova are, they're only part of the story. Beyond them lurk remnants so bizarre, they challenge our very understanding of physics, like the Vela supernova remnant, where a spinning neutron star fires antimatter jets into space, or Puppies A, a shattered stellar corpse glowing with mysteries we've only begun to unravel. Just 22 years after Tycho's supernova stunned the world, another brilliant star appeared in the night sky, this time in the constellation Ophiuchus, dazzling observers including Johannes Kepler, who documented it with such precision that it now bears his name. But unlike Tycho's remnant, which fits neatly into the Type Ia category, Kepler's supernova refuses to be pigeonholed. 4 centuries later, astronomers still grapple with its contradictory clues. Is this the ghost of a white dwarf's thermonuclear demise, or the shattered remains of a massive star's explosive collapse? The mystery lies in the remnant's strange duality. Its outer regions glow with the telltale signatures of a Type Ia explosion, expanding at breakneck speeds, rich in iron and silicon, just like Tycho's. But peer closer, and things get weird. The inner debris field shows unexpected turbulence, with knots of oxygen and neon typically seen in core collapse supernova. It's as if the star couldn't decide how to die, leaving behind a cosmic Rorschach test that challenges our classifications. Some theorize it was a rare, Type Ix supernova, a partial explosion where the white dwarf survived, while others argue it's evidence of a massive star that shed its outer layers before detonating. What makes Kepler's remnant especially fascinating is its environment. Unlike most supernova, which explode into the sparse interstellar medium, this one erupted inside a dense bubble carved by its progenitor's stellar winds. The shockwaves didn't just expand, they collided with this pre-existing cavity, creating overlapping rings of gas that resemble ripples from multiple stones tossed into a pond. X-ray observations reveal where these shock fronts heat surrounding material to millions of degrees, while infrared telescopes uncover cooler dust grains forged in the blast, now drifting like cosmic soot. But perhaps the most tantalizing clue lies in what's missing. Despite meticulous searches, no neutron star or black hole has been found at Kepler's heart, deepening the enigma. If it was a core collapse event, where's the stellar corpse? If it was Type Ia, why does the debris look so unsettled? Every unanswered question forces us to reconsider the boundaries of how stars explode. Kepler's legacy reminds us that nature rarely follows textbook models. Its tangled remnant is a testament to the diversity of stellar deaths, a reminder that every supernova writes its own rules. And as we push deeper into the catalog of celestial aftermaths, we'll encounter remnants that make even Kepler's puzzle seem straightforward, some so ancient they've merged with the galaxy, others so energetic they redefine what we thought possible. In the spring of 1006, observers across the globe witnessed an unprecedented celestial spectacle, a star flaring to life in the constellation Lupus, blazing brighter than anything in the night sky except the moon. Chinese astronomers called it a guest star, while monks in Switzerland described it as wonderful to see. For months, it rivaled Venus in daylight, casting shadows at night, a brilliance we now know came from SN 1006, the brightest supernova in recorded human history. Today, its remnant offers a masterclass in cosmic extremes. Unlike the tangled wreckage of Cassiopeia A or the pulsar-powered Crab SN 1006's debris forms an eerily symmetrical shell, expanding with near-perfect circularity across 30 light-years. But don't let its orderly appearance fool you. This remnant crackles with violence. Its shock fronts accelerate particles to within a hair's breadth of light speed, generating gamma rays so intense they've helped solve a century-old mystery, the origin of cosmic rays that constantly rain down on Earth. What makes SN 1006 truly unique is its textbook shock physics. The remnants' razor-thin filaments act like natural particle colliders, where magnetic fields trap electrons in spiraling paths, causing them to emit synchrotron radiation across the spectrum. This process is so efficient that astronomers have dubbed it a cosmic p-vatron, a reference to the mind-boggling peta-electron volt energies at play. Yet despite this fury, the remnant's uniformity suggests something rare, a remarkably clean, symmetrical explosion, possibly from a white dwarf that detonated without the lopsided instabilities seen in other type Ia supernova. But the real treasure lies in what SN 1006 reveals about our galactic neighborhood. By mapping its debris, scientists discovered it's sweeping up material from a previously unseen interstellar tunnel, a low-density cavity that may explain why the explosion appeared so dazzlingly bright. Less gas meant less light absorption, allowing its brilliance to reach Earth unfiltered. It's a reminder that supernovae aren't just about the dying star. Their visibility depends on the cosmic stage they explode onto. As we piece together SN 1006's story, we're also confronting new puzzles. Why does its southeastern rim glow twice as bright in X-rays? Could hidden turbulence lurk beneath its smooth exterior? Each answer reshapes our understanding of how energy distributes in these stellar explosions, knowledge that's vital for interpreting more distant supernova lighting up galaxies across the universe. Yet for all its brilliance, SN 1006 is just one beacon in a sea of remnants, some so faint they've eluded detection for centuries, others hiding in plain sight, disguised by dust or distance. These overlooked ghosts may hold keys to even deeper mysteries, like how often supernova truly occur in our galaxy, or what strange stellar chemistries they leave behind. Their stories are waiting, written in the quiet glow of gas too cold to see and echoes too faint to hear, until now. Stretching across the constellation Cygnus like a celestial bride's veil, this ethereal remnant tells a story of destruction painted in the soft glow of ionized oxygen and hydrogen. The Veil Nebula isn't just debris, it's a masterpiece of shockwave artistry, where the violence of a supernova has been frozen in time, sculpted into delicate tendrils that span over 100 light-years. To put that in perspective, if you could travel at the speed of light, it would take an entire human lifetime just to cross a fraction of this cosmic wreckage. What makes the Veil so mesmerizing is how it reveals the invisible forces shaping our galaxy. Each filament is a cosmic billboard, lit up by the collision of the supernova's shockwave with pockets of cooler interstellar gas. The brighter regions, like the famous Witch's Broom section, glow fiercely in oxygen emissions, a signpost of gas heated to millions of degrees. Meanwhile, the fainter hydrogen-rich areas trace older, slower-moving material, like echoes of the explosion's first moments. It's as if we're seeing the aftermath of a stellar explosion in ultra-high definition, with every wrinkle and ripple telling us how energy dissipates across the cosmos. But the Veil's true value lies in its role as a natural physics lab. Astronomers have discovered that its shock fronts act like particle accelerators, slinging electrons at near light speeds and generating faint radio waves. These processes mirror what happens in far more extreme environments like the jets of black holes, but here, they're played out on a scale we can study in detail. Even the nebula's expansion, speed around 600,000 kilometers per hour, offers clues about how supernova enrich their surroundings with heavy elements. Peering into its tangled structure is like reading a textbook on interstellar chemistry, written in the language of light. Yet for all its scientific importance, the Veil Nebula also reminds us of the fleeting nature of cosmic beauty. In another few thousand years, its filaments will dissipate further, blending into the galactic background. What we're witnessing is a transient moment in a much longer story, one where destruction gives way to rebirth. The same elements glowing in its tendrils today may one day collapse into new stars, planets, or even life. And as we turn our gaze to other remnants, we'll find that the Veil's elegance is just one variation on a universal theme, that even in death, stars rewrite the destiny of the cosmos around them. Puppies isn't just another supernova remnant, it's a cosmic mystery wrapped in glowing gas and hurtling through space at breakneck speed. Nestled in the constellation Puppies, this sprawling debris field tells the story of a star that exploded roughly 3,700 years ago, leaving behind not just a ghostly nebula, but something far more intriguing, a neutron star racing away at nearly 1,500 kilometers per second. That's fast enough to travel from Earth to the Moon in just 4 minutes. What makes this neutron star, dubbed the cosmic cannonball, so extraordinary isn't just its speed, but the violent story it implies. Most neutron stars sit quietly near the center of their remnants, but this one was violently kicked, likely by asymmetrical forces during the supernova explosion. Imagine a stellar explosion so lopsided it sent its dense core careening through space like a billiard ball struck at an angle. That's the kind of chaos Puppies A's neutron star reveals, a death throes so turbulent it defies our neat models of how stars die. Yet the remnant itself is no less fascinating. Its intricate web of gas glows in X-rays, heated to millions of degrees by shockwaves still rippling outward. Some regions shine with the light of ionized oxygen, while others flicker with the telltale signatures of sulfur and silicon elements forged in the star's final moments. But what really sets Puppies apart is its environment. Unlike many remnants expanding into empty space, this one is plowing through a dense interstellar cloud, creating a spectacular collision zone where hot gas meets cold dust. These interactions make it a natural laboratory for studying how shockwaves transfer energy and even trigger new rounds of star formation. And that's the hidden irony of Puppies A. The same explosion that obliterated a star is now sculpting the ingredients for new ones. As its shockwaves compress nearby gas, they may be laying the groundwork for future stellar nurseries, proof that destruction and creation are eternally linked in the cosmos. But Puppies is just one example of this celestial recycling. Beyond it lie remnants so vast, their shockwaves have become cosmic gardeners, cultivating the next generation of stars in their wake. Deep in the constellation Aquila, a supernova remnant named W44 is rewriting the rules of cosmic recycling, not just as a graveyard for a dead star, but as a bustling nursery where new stars are born. Imagine a shockwave from a stellar explosion slamming into a massive cloud of cold molecular gas with such force that it squeezes the material until pockets collapse under their own gravity, sparking fresh suns into existence. That's exactly what's happening here, destruction giving way to creation in a celestial cycle as old as the universe itself. W44's brilliance lies in its duality. On one hand, it's a classic leftover from a supernova, a turbulent bubble of hot gas expanding at 30 kilometers per second, its outer edges glowing with the telltale signatures of ionized hydrogen and oxygen. But peer closer and you'll spot something extraordinary. Along its western rim, the Remnants shockwaves have plowed into a dense molecular cloud, compressing the gas like snow piling up in front of a plow. Infrared telescopes reveal dozens of young stellar objects embedded in these compressed regions, protostars flickering to life, their infancy directly triggered by the violence of a long-dead star. This isn't just a chance encounter, it's a snapshot of how galaxies evolve. The heavy elements forged in W44 supernova, carbon, nitrogen, and oxygen, are now being woven into the fabric of these newborn stars, ensuring the next generation will have the raw materials for planets and perhaps even life. Even more astonishing, some of these protostars are surrounded by water molecules that were likely vaporized by the explosion, then recondensed as the shockwaves cooled, a cosmic distillation process that might seed future oceans. But W44 has another secret. It's home to a maser, a natural laser created when molecules like hydroxyl amplify radio waves. These intense emissions act as cosmic speedometers, letting astronomers measure how the remnants' energy transfers to surrounding clouds. What they've found defies expectations. The energy isn't dissipating evenly but creating intricate, unpredictable pockets of star formation, like a stone skipping across a pond and leaving frothy turbulence in its wake. This remnant proves that stars don't die in isolation. Their final acts ripple through space, shaping destinies we're only beginning to trace. And as we turn our gaze deeper into the galaxy, we'll find even more dramatic examples of this stellar alchemy, remnants that don't just form stars, but forge the very elements that make our existence possible. If the Veil Nebula is a delicate cosmic tapestry, then the Cygnus loop is its gargantuan cousin, a sprawling, filamentary web that dominates the northern sky like a celestial crown. Stretching across 3 degrees of space, that's 6 full moons side by side, this titanic remnant is what's left of a supernova that detonated somewhere between 10 and 20,000 years ago, when human civilizations were first domesticating wheat and forging tools. Today, its shockwaves still race outward at 300 kilometers per second, sculpting the interstellar medium on a scale so vast, it's reshaped entire star-forming regions in its wake. What makes the Cygnus loop so extraordinary isn't just its size, it's the forensic detail it offers. Unlike younger remnants still roiling with turbulence, this ancient explosion has settled into a phase where its structure tells a clear story. The brightest filaments, glowing in oxygen emissions, trace the outermost shock fronts like the leading edge of a wildfire, while fainter hydrogen-rich tendrils reveal older debris slowing as it interacts with interstellar material. It's a stark contrast to remnants like Cassiopeia A, where chaos still reigns. Here, we see the long-term aftermath of a supernova's energy dissipating into the galaxy. But the Cygnus loop's real value lies in its role as a cosmic historian. By studying how its shockwaves have cooled and fragmented over millennia, astronomers can calculate how much energy the original explosion released, equivalent to 100 million suns shining for an entire month. Even more fascinating are the cooling zones, where hot plasma transitions to lower energies, acting like natural laboratories for understanding how heat dissipates in space. These processes aren't just academic, they dictate how heavy elements disperse, how magnetic fields evolve, and even how future stars might ignite in the remnants' wake. Yet for all its grandeur, the Cygnus loop harbors mysteries. Why do some filaments appear knotted while others stretch smooth as silk? Could undiscovered neutron stars lurk in its uncharted regions? And perhaps most intriguing, what did this explosion look like to early humans? Unlike Tycho's or Kepler's supernova, this one predates written records, leaving us to reconstruct its brilliance from the echo alone. As we shift our gaze from these ancient remnants to younger, more enigmatic ones, we'll encounter explosions that defy even the Cygnus loop's majesty, supernova that leave behind not just glowing gas, but bizarre objects rewriting the rules of physics. From magnetars with magnetic fields strong enough to erase credit cards from light years away, to black holes spinning so fast they warp spacetime itself, the universe's stellar graveyards are far stranger than we ever imagined. Hidden in the dense star fields of the galactic center, a cosmic toddler is throwing a high-energy tantrum, G 1.9 plus 0.3, the youngest supernova remnant ever discovered in our Milky Way. While most remnants we've explored are centuries or millennia old, this one is a mere 150 years young, so recent that its light hadn't even reached Earth when the Industrial Revolution was transforming human civilization. What makes G 1.9 plus 0.3 so extraordinary isn't just its age, it's the unprecedented window it gives us into the chaotic first moments after a star's violent death. Unlike older remnants where shockwaves have slowed and faded, this one is expanding at a staggering 30,000 kilometers per second, roughly 10% the speed of light. That's fast enough to cross the entire United States in less than a tenth of a second. X-ray telescopes reveal a storm of energized particles colliding with interstellar gas, heating it to millions of degrees and lighting up like a cosmic neon sign. But the real treasure lies in the remnant's asymmetry. Its debris isn't spreading evenly but surging outward in violent, lopsided jets, offering clues that the original explosion may have been wildly uneven, perhaps triggered by exotic physics we're only beginning to understand. What's especially fascinating is how this remnant bridges theory and observation. For decades, astronomers modeled supernova based on centuries-old remnants, like reconstructing a fireworks display from drifting smoke alone. But G 1.9 plus 0.3 lets us study the firework mid-explosion. Radio observations show its shockwaves accelerating electrons to near light speed, while infrared data reveals dust grains freshly forged in the blast, some still warm enough to glow. These details help answer lingering questions, like how quickly heavy elements disperse, or why some supernova leave behind messy debris instead of clean shells. Yet this young remnant holds darker mysteries too. Despite its energy, no neutron star or black hole has been detected at its core, raising the possibility that the stellar corpse may have been ejected at tremendous speed, or that the explosion was so violent it left nothing behind. Every new observation peels back another layer, revealing how much we still don't know about stars' final moments. As we shift our gaze from these fledgling remnants to older, more evolved ones, we'll discover how their stories intertwine, how the chaos of youth gives way to the slower, grander processes that shape galaxies over eons. But for now, G 1.9 plus 0.3 stands as a reminder that the universe's most explosive dramas aren't just ancient history, they're unfolding around us, if only we know where to look. In the year 185, Chinese court astronomers recorded an eerie sight, a guest star blazing near Alpha Centauri, glowing for 8 months before fading into obscurity. What they witnessed was one of history's most well-documented supernova, and today, its remnants still linger as RCW 86, a sprawling cosmic wreckage that defies expectations. Stretching over 85 light-years across, this ancient remnant isn't just a relic of the past. It's a puzzle challenging our understanding of how stellar explosions evolve over centuries. What makes RCW 86 so perplexing is its sheer size. Most remnants this old would have dissipated or slowed dramatically, but this one retains shockwaves racing outward at nearly 6 million kilometers per hour. The secret lies in its birthplace, a vast cavity likely carved by the progenitor star's stellar winds long before it exploded. Think of it like a firework detonating inside an empty warehouse instead of a crowded street. With less material to collide with, the debris could expand faster and farther, creating a remnant far larger than typical supernova leftovers. X-ray observations reveal iron-rich regions glowing at 10 million degrees, while infrared telescopes uncover cooler dust grains drifting like cosmic ash, evidence of elements forged in the blast and scattered across interstellar space. Yet RCW 86's greatest surprise came when astronomers compared its modern position with historical records. By tracing back its expansion, they confirmed it's indeed the aftermath of that 185 event, making it the oldest supernova remnant ever linked to human observations. This time capsule lets us study how shocks weaken over millennia and how heavy elements like silicon and sulfur mix with surrounding gas. But here's the twist: the remnant's shape suggests the explosion wasn't symmetrical. Some debris races ahead in fierce jets, while other regions lag behind, hinting that the dying star may have spun wildly or erupted with lopsided force. This remnant forces us to rethink supernova as not just uniform explosions, but chaotic events shaped by their environments. The same winds that hollowed out its cavity may have also altered the star's death throes, creating a feedback loop between a star's life and its demise. And as we turn to other remnants, we'll find even more striking variations, explosions that leave behind diamond-like pulsars, warp spacetime into black holes, or vanish without a trace. Each one proves that when stars die, they don't just fade away, they rewrite the rules of the cosmos around them. Nestled in the large Magellanic Cloud, our galaxy's spirited neighbor, N132d isn't just another supernova remnant. It's a cosmic emissary from another stellar community, offering a rare chance to study stellar death beyond the Milky Way's borders. What makes this remnant extraordinary isn't just its distance, but its dazzling oxygen-rich filaments, glowing like celestial neon signs against the velvet dark of intergalactic space. Unlike the symmetrical shells of remnants like SN 1006, N132D's chaotic, lopsided shape tells a story of uneven destruction, hinting that its progenitor star may have erupted in a violently asymmetrical explosion, flinging debris in wild, unpredictable directions. The real value of studying N132D lies in its role as a cosmic control experiment. By examining remnants in other galaxies, astronomers can separate universal patterns of stellar death from quirks unique to our galactic environment. Here, the oxygen-bright filaments aren't just beautiful, they're forensic evidence of the star's final nuclear reactions, preserved in a low metallicity environment unlike anything in our own galaxy. The absence of heavy elements like iron in certain regions suggests this might have been a rare, pair instability supernova, a theorized explosion so powerful it obliterates the star entirely, leaving no neutron star or black hole behind. But N132D's surprises don't end there. Infrared observations reveal vast dust clouds within the remnant particles forged in the explosion itself, now drifting like cosmic soot. This dust isn't just debris, it's the raw material for future planets, confirming that even in other galaxies, supernova seed the universe with the building blocks of worlds. Meanwhile, X-ray telescopes detect shock waves racing through the remnant at 7,000 kilometers per second, heating gas to temperatures that mimic conditions moments after the Big Bang. It's as if N132D has bottled the chaos of creation itself, letting us study physics at extremes impossible to replicate on Earth. Yet what's most humbling about this distant remnant is its perspective shift. By seeing stellar death through an intergalactic lens, we're reminded that the laws of physics play out the same everywhere, whether in our backyard or a galaxy 160,000 light-years away. And as our search expands, we'll encounter remnants so faint or bizarre they test the very limits of detection, echoes of explosions that might rewrite our understanding of how stars die across the cosmos. Just 1,200 light-years from Earth, practically our cosmic backyard, the Vela supernova remnant sprawls across the night sky with the grace of a shattered stellar chandelier. This isn't some distant spectacle glimpsed through telescopes. It's a front-row seat to the aftermath of a star's violent death, so close that amateur astronomers can spot its faint glow with backyard equipment. What makes Vela extraordinary isn't just its proximity, but the way its pulsar, a city-sized neutron star spinning 11 times per second, acts like a frantic lighthouse, sweeping the cosmos with twin beams of radiation that flicker with metronomic precision. Peering into Vela's wreckage is like examining a fossilized explosion in ultra-high definition. Its filaments, some glowing blue with X-rays while others shimmer red in visible light, trace where the shockwave plowed into interstellar gas, heating it to millions of degrees. But the real marvel lies in the asymmetry of the debris. Unlike textbook remnants with neat spherical shells, Vela's structure resembles a crumpled paper bag, evidence that the original explosion may have blasted material outward in uneven jets. This chaos isn't random, it's a snapshot of how a dying star's magnetic fields or rotation can sculpt its own destruction. What truly sets Vela apart, though, is its pulsar's antics. This hyperactive stellar corpse doesn't just spin its rockets through space at over 1 million kilometers per hour, trailing a comet-like tail of high-energy particles visible in gamma rays. Some astronomers suspect this speed comes from a natal kick during the supernova, a recoil so violent it flung the neutron star clear of the remnant's center. The pulsar's jets, meanwhile, carve through surrounding gas like cosmic blowtorches, creating intricate loops and knots that resemble ghostly fingerprints. Yet Vela's greatest gift might be its intimacy. Because it's so close, we can study processes usually blurred by distance, like how shockwaves gradually slow as they sweep up interstellar material, or how dust grains forged in the explosion disperse over millennia. Even the remnant's age, roughly 11,000 years, offers a Goldilocks window, old enough for the debris to have expanded into intricate structures, yet young enough that its energy hasn't fully dissipated. It's a living laboratory for understanding how supernova enrich their neighborhoods, seeding space with elements that might one day form new worlds. But as familiar as Vela feels, it's just the tip of the cosmic iceberg. Beyond it lie remnants that defy even these breathtaking standards, explosions so energetic they warp the fabric of space-time, or so ancient they've merged with the galaxy itself. These outliers don't just challenge our models, they force us to rethink what's possible when stars reach the end of their lives. In the constellation Cygnus, a celestial powerhouse hides within the tangled wreckage of MSH 1552, a supernova remnant whose beating heart isn't just a neutron star, but a frenetic dynamo blasting the cosmos with a hurricane of high-energy particles. Unlike the relatively sedate pulsar at the Crab Nebula's core, this one spins with reckless abandon, whipping charged particles into a vast, luminous nebula that stretches over 150 light-years. Imagine a lighthouse not just shining light, but hurling entire storms of radiation into space. That's the kind of cosmic engine we're dealing with here. What makes MSH 1552 truly exceptional is how its pulsar wind nebula acts like a time machine. The neutron star's furious energy output, powered by its immense magnetic fields, creates shock fronts that glow brightest where particles slam into older debris from the original explosion. By mapping these collisions, astronomers can essentially rewind the remnants' evolution, tracing how pulsar winds sculpt their surroundings over centuries. X-ray telescopes reveal intricate loops and tendrils where magnetic fields channel particles at near light speed, while gamma-ray observations detect even more extreme processes: electrons smashing into photons and boosting them to staggering energies. Yet the real marvel lies in the pulsar's sheer audacity. Named pulsar B 1509-58, this city-sized object spins 7 times per second, its magnetic field a mind-bending 15 trillion times stronger than Earth's. That's enough to shred atoms from light years away. The energy it pumps into its surroundings doesn't just illuminate gas, it redefines the very physics of the region. Some particles in its wind nebula reach energies so high, they challenge our models of how neutron stars accelerate matter, hinting that something even stranger might lurk in these magnetic maelstroms. MSH 1552 isn't just a static relic, it's a dynamic laboratory where the universe flexes its most extreme forces. As we turn our gaze to other remnants, we'll find that this interplay between pulsars and their debris is no fluke. It's a recurring theme in the cosmos, where the dead stars of yesterday become the architects of tomorrow's celestial landscapes. At first glance, the Ant Nebula looks like it could belong among our catalog of supernova remnants. Its glowing, bipolar jets stretching light years into space resemble the shockwaves of a stellar explosion. But this cosmic mimic reveals a far gentler truth. It's actually a planetary nebula, the final breath of a star no more massive than our Sun. While both phenomena paint the cosmos with luminous gas, their origins couldn't be more different. Where supernova remnants are born from violent detonations, planetary nebulae like the Ant Nebula emerge when aging stars shed their outer layers in slow, shimmering waves, leaving behind a white dwarf that lights up the expelled gas like a lantern in fog. The key to telling them apart lies in the details. Supernova remnants race outward at thousands of kilometers per second, their shock fronts churning with heavy elements forged in the explosion. Planetary nebulae, by contrast, expand leisurely, their chemical fingerprints rich in helium and nitrogen, artifacts of the star's surface layers rather than its core. Even their light tells different stories. The Ant Nebula's delicate filaments glow predominantly from ionized oxygen and nitrogen, while supernova debris often blazes with X-rays from colliding particles accelerated to extreme energies. Yet the Ant Nebula isn't just a case of mistaken identity, it's a masterpiece of stellar artistry. Its symmetrical, hourglass shape hints at unseen forces, likely sculpted by the dying star's magnetic fields or an orbiting companion star's gravitational pull. This intricate structure offers a counterpoint to the chaos of supernova, proving that even modest stars can paint the cosmos with breathtaking precision. Astronomers rely on tools like spectroscopy to decode these celestial doppelgangers, analyzing the light's wavelengths to unravel their true natures. But sometimes the universe delights in blurring the lines. Some objects, like the enigmatic Saccuri's object, start as planetary nebulae before undergoing late-stage eruptions that mimic supernova, challenging our neat classifications. These outliers remind us that the cosmos resists simple labels, inviting us to look deeper, question assumptions, and embrace the beautiful complexity of stellar life cycles. As we refine our cosmic census, each misidentified remnant or nebula becomes a lesson in humility, a nudge to sharpen our tools and expand our understanding. And waiting in the wings are even greater puzzles, remnants that defy all known models, explosions that leave no visible traces, and stellar ghosts that flicker at the edge of detection. Their stories will test the very frameworks we use to make sense of the universe's grand narrative. DML 316 is a cosmic illusionist, playing tricks on astronomers with its baffling double identity. For years, this sprawling cloud of gas and dust in the Large Magellanic Cloud appeared to be two distinct supernova remnants, until closer inspection revealed an even stranger truth. What we're actually seeing is a single, misshapen structure twisted by forces we're only beginning to understand. The overlapping shells of debris don't mark separate explosions, but rather the aftermath of one star's violent death interacting with an invisible interstellar obstacle course. This remnant's bizarre morphology is like a Rorschach test for astrophysicists. Some regions glow with the characteristic X-ray signature of shock-heated gas, while others flicker with radio waves from particles accelerated to extreme energies. The key clue came when researchers noticed the two remnants shared identical expansion speeds and chemical compositions, telltale signs they were sculpted by the same cataclysm. The current leading theory, the original supernova blast slammed into a dense, pre-existing cavity, perhaps carved by the progenitor star's own stellar winds, creating reflections and echoes that mimicked a second explosion. It's as if the universe folded a cosmic piece of paper, leaving us to decipher the creases. What makes DML 316 especially valuable is how it exposes the limits of our cosmic detective work. Without three-dimensional vision across light years, astronomers must reconstruct stellar explosions from two-dimensional snapshots, where overlapping structures can create optical illusions. This remnant forces us to question assumptions when we see multiple shells. Are we witnessing separate events, or just the complex interplay of shockwaves and their environments? The answer often lies in chemistry. By analyzing the distribution of elements like silicon and iron, scientists can trace debris patterns back to their origins, distinguishing between multiple explosions and single, distorted ones. Yet DML 316's greatest lesson might be about cosmic recycling. Within its tangled filaments, telescopes have spotted vast amounts of freshly forged oxygen and neon elements that will eventually mix with interstellar clouds, enriching future generations of stars and planets. This isn't just debris, it's stardust in transit, carrying the ingredients for new worlds. And as we turn our gaze to other remnants, we'll find even more dramatic examples of this stellar alchemy, where explosions don't just destroy, but disperse the very elements that make life possible. 3C58 isn't your typical supernova remnant. It's a cosmic rebel with a neutron star that refuses to follow the rules. While most pulsars blast X-rays into space like lighthouses, this one whispers faintly, emitting just a fraction of the radiation astronomers expect. nestled within intricate filaments that glow like celestial lace. Its enigmatic core challenges everything we thought we knew about how neutron stars age and evolve. The mystery deepens when you compare 3C58 to its famous cousin, the Crab Nebula's pulsar. Both remnants were born from supernova observed centuries ago, the Crab in 1054, and 3C58 potentially linked to a stellar explosion witnessed in 1181. Yet their neutron stars couldn't behave more differently. The Crab's pulsar spins furiously, bathing its surroundings in high-energy radiation, while 3C58's remains strangely subdued. Some theories suggest its magnetic field has decayed unexpectedly fast, or that its interior cooled through exotic quantum processes we don't fully understand. Others speculate it might harbor a superfluid core where particles flow without friction, sapping energy from the star's rotation, but the remnant's secrets aren't just hidden in its silent neutron star. Its sprawling debris field tells its own tantalizing story. Delicate filaments, rich in oxygen and sulfur, twist through the nebula like frozen smoke, sculpted by magnetic fields strong enough to bend atoms. Meanwhile, radio observations reveal vast lobes of particles stretching light years into space, evidence of past jets that once roared from the pulsar but now seem eerily quiet. This stark contrast between past fury and present calm suggests neutron stars might evolve along multiple paths, with some fading gently while others rage against the dying of the light. Perhaps the most profound lesson of 3C58 is how much we still don't know. Every anomaly forces us to reconsider textbooks, reminding us that the universe thrives on variety. As we push further into the catalog of remnants, we'll encounter even more extreme environments, where magnetic fields warp spacetime itself, and temperatures reach levels unseen since the Big Bang. These cosmic outliers don't just defy expectations, they rewrite the rules of physics in real time. The Calabash Nebula isn't waiting for death, it's rehearsing for it. This turbulent cosmic spectacle, also known as the Rotten Egg Nebula for its sulfur-rich chemistry, offers astronomers a rare dress rehearsal for the final act of a star's life. Unlike the remnants we've explored so far, this isn't debris from an explosion, it's the prelude, where a dying sun-sized star violently sheds its outer layers in erratic, mushroom-shaped clouds at speeds topping 1 million kilometers per hour. What makes the Calabash Nebula so fascinating is how it bridges the gap between peaceful planetary nebulae and catastrophic supernova. Twin jets of gas scream outward in opposite directions, sculpted by the star's spin or perhaps an unseen companion's gravity, while concentric rings of ejected material ripple through space like smoke from a cannon. But the real showstopper is its chemistry. Unlike typical stellar outflows dominated by hydrogen and helium, this nebula pumps out bizarre molecules like sulfuric compounds and even water vapor, creating conditions more akin to interstellar chemistry labs than quiet stellar retirement. These chaotic outflows hint at what might be brewing in the star's core. As it exhausts its nuclear fuel, the dying star experiences violent convulsions, thermal pulses that eject material in fits and starts, rather than the smooth, glowing halos seen in gentler planetary nebulae. Some astronomers speculate the Calabash might one day collapse into a white dwarf like its calmer cousins, while others wonder if its instability could lead to a spectacular supernova, leaving behind an entirely different kind of remnant. Studying this cosmic oddity is like finding an artist's preliminary sketches. It reveals the creative process underlying stellar destruction. The same turbulence shaping its billowing clouds today might dictate whether tomorrow's remnants form symmetrical shells or chaotic debris fields. And as telescopes uncover more objects in this transitional phase, we're beginning to see how a star's final years could determine the afterlife it leaves behind, whether that's a quiet white dwarf, a swirling pulsar nebula, or something even more extraordinary. Beyond the Calabash lie remnants that defy all these expectations, cosmic enigmas where the rules of stellar death seem rewritten entirely. These outliers don't just challenge our models, they force us to reconsider what's possible when stars reach their breaking point. G292, 0 plus 1, 8 is like a cosmic neon sign blazing with revelations, a supernova remnant so rich in oxygen that it glows like a celestial fingerprint of stellar alchemy. Nestled in the constellation Centaurus, this expanding debris field offers more than just a spectacle. It's a time capsule preserving the final moments of a massive star's explosive death. What makes this remnant extraordinary isn't just its dazzling oxygen filaments, though they do shine with the intensity of a star's last nuclear breaths, but the clues it holds about how the universe forges the very elements that make life possible. The magic of G292, 0 plus 1, 8 lies in its asymmetry. Unlike remnants with neat spherical shells, this one sprawls in lopsided tendrils, suggesting the original explosion was anything but orderly. At its heart, a pulsar races through space, spinning 15 times per second, a silent witness to the chaos that birthed it. The interplay between this neutron star and the surrounding debris is a forensic goldmine. X-ray telescopes reveal pockets of magnesium, neon, and silicon mixed with the oxygen, creating a chemical map that traces the star's internal layers moments before detonation. It's as if we're sifting through the shrapnel of a cosmic bomb, reconstructing how heavy elements were synthesized under extreme pressures and temperatures. But the real treasure here is what the oxygen tells us. This element so vital for water, breathable air, and the chemistry of life was forged in the star's fiery core and then blasted into space by the supernova. By studying its distribution, astronomers can pinpoint exactly how much oxygen a single massive star contributes to the galactic reservoir. The numbers are staggering. This one explosion likely scattered enough oxygen to seed thousands of future solar systems. And because the remnant is relatively young, just a few thousand years old, we're seeing these elements before they've fully mixed with interstellar gas, offering a rare snapshot of enrichment in progress. Yet G292, 0 plus 1, 8 isn't just about the past. Its pulsar's relentless energy continues to shape the remnant, accelerating particles to near light speed and creating shock fronts that glow across the electromagnetic spectrum. These dynamic processes are a live demonstration of how supernovae keep giving long after their initial fury fades, energizing their surroundings, triggering new rounds of star formation, and weaving heavy elements into the fabric of future worlds. As we turn our gaze to other remnants, we'll encounter explosions that push shockwave physics to its limits, where debris moves at unimaginable speeds, or where the very shape of the remnant defies conventional models. But G292, 0 plus 1, 8 will always stand out as a reminder that the universe's most destructive moments are also its most creative, scattering the seeds of life amid the chaos. The Jellyfish Nebula drifts through space like its namesake, an ethereal cosmic creature with tendrils that glow against the void. Officially catalogued as IC 443, this supernova remnant isn't just another cloud of debris, it's a celestial collision in progress, slamming into a dense molecular cloud with enough force to light up the interstellar dark. The result, a shimmering, tangled web of gas where shockwaves heat material to millions of degrees, making it fluoresce in vivid X-rays while cooler regions glow with the soft light of hydrogen and oxygen. It's a textbook example of how remnants don't fade quietly. They reshape their surroundings, leaving behind radiant fingerprints of their passage. What makes the jellyfish so mesmerizing is the way its structure tells a story in layers. The nebula's eastern edge shows crisp, sharp filaments, evidence of shockwaves plowing into undisturbed gas like a snowplow through fresh powder. Meanwhile, the western side is a messier affair, where the explosion's energy has encountered resistance from the molecular cloud, creating turbulent knots and bubbles that resemble the jellyfish's stinging tentacles. This asymmetry isn't chaos, it's a forensic record of the remnant's environment. By studying these variations, astronomers can reconstruct the density and motion of the cloud the star exploded into, almost like reading ripples in a pond to guess where the stone was tossed. But the real treasure here is hidden in plain sight, a neutron star racing away from the explosion's epicenter at over 300 kilometers per second. This stellar fugitive, known as Sizu J061705, 3 + 222,127, is the exclamation point at the end of the jellyfish's story, proof that supernova don't just leave behind glowing gas, but often kick their collapsed cores into motion with unimaginable force. The neutron star's trajectory traces back to the remnant's geometric center, confirming its origin, while its faint X-ray pulsations hint at the magnetic turmoil churning beneath its surface. Yet the jellyfish's greatest lesson might be about cosmic recycling. The same shockwaves lighting up its tendrils are also compressing pockets of gas within the molecular cloud, potentially triggering new star formation. It's a paradoxical twist, the death of one star catalyzing the birth of others, weaving destruction and creation into a single celestial tapestry. And as we venture deeper into the catalog of remnants, we'll encounter even more extreme examples of this interplay, where supernova don't just illuminate the darkness, they sculpt it. Stretching across the constellation Taurus like a celestial tangle of luminous spaghetti, Cygnus 147 defies every expectation of what a supernova remnant should look like. This cosmic labyrinth spans an astonishing 150 light-years, so vast that if placed at the center of our solar system, its filaments would brush against the nearest stars. Unlike the orderly shells of younger remnants, Cygnus 147's chaotic web of glowing hydrogen filaments suggests an explosion of extraordinary violence, where shockwaves rip through space with such ferocity that the debris field resembles a shattered stained glass window frozen mid-explosion. Peering into this remnant is like stepping into a cosmic forensic lab. The filament's twists and knots reveal where the blast wave encountered pockets of denser interstellar material, creating shock fronts that glow in vivid reds and pinks. But what truly baffles astronomers is the remnant's apparent age, estimated at around 40,000 years, making it far older than most studied supernova remnants. Despite its advanced years, Cygnus 147 shockwaves still race outward at several hundred kilometers per second, a testament to the sheer energy unleashed in the original detonation. This longevity offers a rare chance to study how remnants evolve over millennia, gradually transferring their energy back into the galaxy. The most compelling mystery, though, lies in its possible origin. Some researchers speculate this tangled wreckage might be the aftermath of not one, but two stellar explosions, a cosmic collision where shockwaves from separate supernovae intertwined over centuries. Others suggest the progenitor star itself was unusually dynamic, perhaps part of a binary system that altered the explosion's symmetry. Clues hide in the remnants' chemical fingerprints. Regions rich in sulfur and oxygen trace the star's final nuclear reactions, while the absence of a visible neutron star hints that the core may have collapsed into a black hole or been flung into deep space. Yet Symai's 147 greatest gift might be how it reshapes our understanding of cosmic feedback. As its shockwaves sweep up interstellar gas, they compress and heat it, potentially triggering new star formation even as the remnant itself fades. This delicate dance between destruction and creation plays out over tens of thousands of years, reminding us that stellar deaths aren't in points, they're turning points in the galaxy's life cycle. And as we shift our gaze from these ancient remnants to younger, more magnetically charged ones, we'll discover explosions that don't just light up the cosmos, but twist its very fabric with forces strong enough to bend reality itself. The Mouse Nebula isn't just a static cloud of stellar debris, it's a cosmic speed demon with a pulsar hurtling through space so fast, it's literally dragging a storm of particles behind it like the tail of a comet. Officially known as G359, 23082, this bizarre remnant gets its nickname from its striking shape, a bright, compact head formed by the pulsar itself, followed by a long, luminous trail stretching 13 light-years across the interstellar void. Imagine a bullet tearing through fog, leaving a swirling wake. That's the kind of kinetic energy we're talking about here. What makes the Mouse truly extraordinary is the sheer velocity of its neutron star, clocked at over 6 million kilometers per hour. At that speed, you could race from Earth to the Moon in under 4 minutes. This breakneck motion isn't just for show, it's a smoking gun for one of supernova's best-kept secrets, asymmetric explosions. When massive stars die, the detonation isn't always a clean, spherical blast. If the collapse is lopsided due to rotation, magnetic fields, or other factors, the resulting natal kick can launch the neutron star like a cosmic cannonball, explaining why some pulsars, like the Mouse's, wind up far from where they were born. But the real magic lies in the tail. As the pulsar barrels through space, its powerful magnetic field whips charged particles into a frenzy, accelerating them to near light speed and creating a shockwave that lights up the surrounding gas. X-ray telescopes reveal this trail, glowing with the energy of a particle accelerator the size of a solar system, while radio observations show how the pulsar's wind interacts with interstellar material, sculpting it into intricate structures. It's a rare chance to study how neutron stars redistribute energy long after their parent explosions fade, yet the Mouse Nebula's greatest lesson might be about time. Most remnants we've explored are either freshly chaotic or ancient and diffuse, but here, we're witnessing a middle-aged system caught in the act of transformation. The pulsar's trajectory suggests the original supernova occurred roughly 80,000 years ago, placing it in a sweet spot where the debris hasn't fully dissipated, but the dynamics have settled enough to reveal underlying physics. By analyzing how the tail wavers or brightens, astronomers can reconstruct the density of the interstellar medium it's traversing, like reading cosmic tea leaves to map the galaxy's hidden structure. As we shift our gaze to even older remnants, we'll encounter explosions so ancient their light has faded, leaving only whispers in the form of gamma-ray echoes or distorted magnetic fields. These time-worn relics don't just challenge our perception of cosmic chronology, they force us to ask whether some supernova vanish entirely, or if we're simply learning to listen for their stories in new ways. The Lupus loop drifts across the sky like a whisper from the distant, past a ghostly imprint of a stellar explosion, so ancient its light has nearly faded from view. Stretching over 100 light-years through the constellation Lupus, this vast remnant isn't the flashy spectacle of younger supernova remnants. It's a study in cosmic patience, its delicate filaments glowing faintly in hydrogen alpha light, visible only through long-exposure photography or sensitive telescopes. What makes this structure so captivating isn't just its size, though it could engulf dozens of solar systems, but what its quiet persistence reveals about how remnants dissolve back into the galaxy over millennia. Unlike the violent shock fronts of Cassiopeia or the intricate lacework of the Veil Nebula, the Lupus loop's beauty lies in its subtlety. Its shockwaves have slowed to a comparative crawl, gently interacting with the interstellar medium rather than tearing through it. This serene phase lets astronomers observe how remnants transfer their final energy back into space, like ripples fading in a pond. Some of its outer filaments are so diffuse they blend into the galactic background, while denser knots still fluoresce with traces of ionized oxygen, chemical echoes of the star's final moments. The real challenge with studying the Lupus loop is its age. Estimated at tens of thousands of years old, it occupies a twilight zone between vibrant young remnants and those that have fully dispersed. Without the intense radiation of a central pulsar or the heat of recent collision fronts, it offers a rare glimpse into the retirement phase of stellar explosions. Radio telescopes have mapped its faint synchrotron radiation, revealing where electrons once accelerated to near light speed now leisurely spiral through fading magnetic fields. Even its shape, a distorted, incomplete shell, hints at the unevenness of the interstellar medium it's expanding into, like smoke encountering a breeze. But the Lupus loop's quiet demeanor belies its scientific value. By analyzing how its structure erodes, astronomers can calculate how much enriched material, carbon, nitrogen, even traces of iron, it's returned to the galaxy, seeding future generations of stars and planets. It's a reminder that supernovae don't just vanish, they become part of the cosmic ecosystem, their atoms destined for new worlds. And as we turn from these ancient, fading remnants to their hyperactive counterparts, we'll encounter explosions that defy such gentle endings, events where stars don't just die, but detonate with forces that push the limits of physics itself. The intricate lacework of S-147 isn't just a beautiful cosmic accident, it's a scrambled message from a stellar explosion that defies simple explanations. Unlike the crisp, spherical shells of younger remnants, this ancient debris field twists through space in chaotic filaments, as if the dying star couldn't decide how to detonate. The closer astronomers study its knotted structure, the more it seems to whisper a tantalizing secret. This wasn't the death of a solitary star, but the violent finale of two stars locked in a gravitational dance. The binary star theory isn't just poetic speculation, it's grounded in S-147's peculiar chemistry and motion. Some filaments race outward faster than others, hinting at uneven forces during the explosion, while pockets of enriched material suggest one star may have siphoned layers from its companion before both met their fiery end. Imagine a celestial tango where one partner's instability triggers catastrophe, distorting the explosion's shape and scattering debris in wild, asymmetrical patterns. This could explain why no neutron star or black hole has been found at the remnant's heart. Perhaps the collapse was so disrupted that the stellar corpses were flung into deep space, leaving only their tangled wreckage behind. Yet S-147's greatest intrigue lies in what it reveals about cosmic diversity. Not all supernovae follow the script. Some, like this one, are messy improvisations where interactions between stars rewrite the rules of stellar death. The Remnants' twisted filaments act as a frozen snapshot of those chaotic final moments, offering clues about how binary systems alter explosions, knowledge that's vital for interpreting similar remnants across the galaxy. As we piece together S-147's fractured history, we're also confronting a broader truth. These explosions aren't just destructive events. Their shockwaves act as natural particle accelerators, funneling unimaginable energy into cosmic rays that streak through the universe at near light speed. And in the next chapter of our journey, we'll encounter remnants where this process isn't just a side effect, it's the main event, with shockwaves so powerful they can hurl atomic particles across galactic distances, seeding the cosmos with the very radiation that shapes its evolution. The Monogem ring isn't just another supernova remnant, it's a cosmic architect that may have shaped the very space around us. Drifting just 900 light-years from Earth, this vast, faint shell of gas stretches across the constellation Gemini like a half-remembered echo of stellar violence. But what makes it truly remarkable isn't its size or its glow. It's the growing evidence that this ancient explosion helped carve out the local bubble, a cavernous region of sparse, hot gas that envelops our solar system and dozens of nearby stars. Imagine a stellar detonation so powerful its shockwaves blew a clearing in the interstellar medium, a celestial snowplow pushing aside gas and dust to create the galactic neighborhood we call home. The connection between Monogem and the local bubble isn't just poetic speculation. Astronomers have traced the remnants' expansion back in time, finding its age, roughly 100,000 years, aligns eerily well with the bubble's formation period. Its shockwaves would have swept through space at supersonic speeds, compressing surrounding material into dense walls while leaving behind the hot, diffuse cavity we now drift through. X-ray observations reveal the bubble's interior is filled with million-degree plasma, scorching evidence of past supernova activity, while the sun's motion through the galaxy suggests we entered this cleared-out zone around the same time Monogem's waves were still reverberating. But here's the twist: Monogem might not have acted alone. Recent studies suggest multiple supernovae, perhaps a chain reaction from a single star-forming region, could have collaborated to sculpt the local bubble's complex structure. The remnants' faint, fractured rings hint at this layered history, with some debris clouds moving faster than others, like ripples from stones tossed into a pond at different times. This collaborative cosmic landscaping reveals how supernova don't just destroy, they engineer environments where future stars and their planets can thrive. The real magic lies in the details. Spectroscopy of Monogem's filaments shows elevated levels of ionized oxygen and neon telltale signatures of a massive star's explosive death. These elements now suffuse the local bubble, mingling with the solar wind and interstellar dust that occasionally breezes through our heliosphere. It's a humbling thought. The air we breathe, the atoms in our hands, may have been stirred and enriched by this very explosion's aftermath. As we turn from local cosmic history to grander symmetries, we'll encounter remnants that don't just shape pockets of space, but reflect the universe's hidden pattern structures where explosions align with mathematical precision, as if the cosmos itself prefers order amid the chaos. These echoes of stellar death don't just light up the night, they inscribe the rules of reality into the fabric of space and time. DA 530 isn't just another supernova remnant, it's a cosmic magnet's dream, a rare celestial artifact where magnetic fields align with eerie precision against the chaos of stellar destruction. While most remnants resemble tangled webs of debris with magnetic fields twisted beyond recognition, this enigmatic structure in the constellation Cygnus glows with an unexpected order, its field lines stretched outward like the spokes of a wheel. This isn't just a quirk of nature, it's a goldmine for scientists probing one of the universe's great mysteries: how cosmic magnetism survives, evolves, and even strengthens in the aftermath of unimaginable violence. What makes DA 530 so puzzling is the stark contrast between its serene magnetic architecture and the turbulent forces that shaped it. When massive stars explode, their magnetic fields are typically shredded and scrambled by the blast. Think of a hurricane tearing through a spiderweb. Yet here, radio telescopes reveal a remarkably coherent pattern, with field lines radiating smoothly across the remnant's shell. One theory suggests the progenitor star's own rotation imprinted this order onto the explosion, like a spinning top transferring its motion to the air around it. Another possibility, the remnant's expansion into a particularly uniform patch of interstellar space somehow preserved, or even amplified, the original magnetic structure. This cosmic anomaly isn't just a curiosity, it's a Rosetta Stone for decoding how magnetic fields influence everything from particle acceleration to galactic evolution. DA 530 orderly fields act like a natural particle collider, channeling electrons along precise paths and causing them to emit synchrotron radiation, a glow that reveals the invisible magnetic landscape. By studying how these fields interact with the remnant's shock waves, astronomers can test theories about how cosmic rays, those high-energy particles bombarding Earth from deep space, get their incredible speed. Yet DA 530's greatest lesson might be about rarity itself. For every remnant like this, there are hundreds with chaotic magnetism, suggesting that such well-ordered fields require a perfect storm of stellar conditions and environmental luck. That makes this celestial oddity not just a scientific treasure, but a reminder of how much variety hides in the aftermath of stellar deaths. And as we push further into the catalog of remnants, we'll encounter explosions where magnetism doesn't just organize particles, it warps them into energies that defy conventional physics, pushing the limits of how we understand the universe's most violent events. HB3 isn't just a ghostly echo of a stellar explosion, it's a cosmic bulldozer plowing through one of the galaxy's densest construction zones. This sprawling remnant in the constellation Cassiopeia has slammed into a massive molecular cloud, creating a fireworks display of shock-heated gas and turbulent chemistry. Picture a tsunami crashing into a coastline, but instead of water, it's a wall of stellar debris moving at 6 million kilometers per hour, and instead of cliffs, it's a nebula packed with enough raw material to build thousands of stars. The collision zone glows in vivid X-rays and radio waves, lighting up like a neon sign where the fury of a supernova meets the stubborn resistance of interstellar gas. What makes this interaction so extraordinary is how it acts as a natural laboratory for two fundamental cosmic processes. First, the shockwaves compress pockets of molecular hydrogen within the cloud, squeezing them until gravity takes over, the very recipe for star formation. Infrared telescopes have already spotted young stellar objects flickering to life along HB3 edges, cosmic infants whose existence was likely triggered by the remnant's violent advance. Second, the heat and pressure at the collision front forge molecules that shouldn't survive in the harsh environment of a supernova remnant: complex carbon chains, silicon oxides, even traces of water vapor. It's as if the explosion's chaos and the cloud's cold chemistry have struck an unlikely truce, creating a temporary workshop for interstellar alchemy. But HB3's greatest revelation might be its timeline. Unlike Remnants expanding into empty space, this one's encounter with the molecular cloud has dramatically slowed its shock fronts, freezing the action in a way that lets astronomers study the interaction in unprecedented detail. The Remnants' eastern edge, where it meets the densest gas, flares brightly in oxygen emissions, while the less obstructed western side races ahead, distorting the debris into a lopsided bubble. This asymmetry provides a real-time lesson in how supernovae redistribute energy, sometimes gently nudging star-forming regions into action, other times violently shredding them apart. Yet for all its destructive power, HB3 is ultimately a creator. The same shockwaves that tear through molecular clouds also seed them with heavy elements forged in the progenitor star's death throes: iron, sulfur, and magnesium that will one day be incorporated into new planetary systems. It's a paradox written across the cosmos, destruction paving the way for creation, chaos giving rise to order. And as we venture deeper into the catalog of Remnants, we'll encounter explosions that push this dynamic to even greater extremes, where stellar deaths don't just alter their surroundings, but engineer conditions so intense they warp the very laws of physics. CTB-1 drifts through Cassiopeia like a celestial riddle written in glowing gas, a supernova remnant shaped uncannily like a question mark, as if the cosmos itself is asking us to solve its mystery. Unlike the symmetrical shells of younger remnants, this twisted loop of ionized filaments stretches nearly 30 light-years across, its curve broken by strange kinks and gaps that defy simple explanation. Some astronomers speculate its bizarre morphology stems from a binary star system torn apart by the supernova, while others suggest the explosion plowed through an unusually lumpy patch of interstellar medium, distorting the shockwaves like wind bending a candle's flame. The intrigue deepens when you examine CTB-1's hidden architecture. Radio telescopes reveal a compact, crescent-shaped band of emission, likely the remnant's forward shock, while the trailing filaments seem almost shredded, as if something disrupted their expansion. At the heart of this cosmic punctuation mark, no neutron star pulses detectably, raising the possibility that the progenitor's core collapsed into a black hole or was ejected entirely. But the most tantalizing clue comes from the remnant's motion. CTB-1 isn't drifting aimlessly but racing through space at an unusual velocity, hinting that its explosion might have been lopsided enough to give the stellar corpse a powerful kick. What makes this remnant truly special isn't just its shape, it's the way it challenges our assumptions about how stars die. Most supernova models predict relatively orderly debris fields, yet CTB-1's tangled structure suggests its progenitor didn't follow the script. Was it a massive star that shed layers asymmetrically before exploding, or could two stars have orbited so closely that their mutual gravity twisted the detonation into this peculiar form? Every observation peels back another layer of mystery, proving that stellar deaths are as unique as the stars themselves. Yet CTB-1's greatest gift might be its role as a bridge to the universe's shadowy extremes. As we turn our gaze to other remnants, we'll encounter explosions that don't just leave behind glowing gas, they illuminate the invisible scaffolding of space itself, revealing dark matter's grip, spacetime's curvature, and forces beyond our current understanding. These cosmic beacons don't just mark where stars perished, they light the path to discoveries we've yet to imagine. G65, 3 + 5, 7 drifts through the cosmos like a whisper in a thunderstorm, a supernova remnant so faint it barely registers against the glow of the Milky Way. Yet this subtle cosmic specter holds surprises that outshine its modest appearance. Discovered not through its visible light, but by the faint radio waves and X-rays rippling from its structure, this low-surface brightness ghost challenges astronomers with a tantalizing paradox. How can something so dim tell us so much about the universe's most violent explosions? The secret lies in its simplicity. Unlike younger, turbulent remnants where shockwaves collide in chaotic brilliance, G65, 3 plus 5, 7's shock fronts have expanded almost undisturbed for roughly 20,000 years. This pristine propagation lets scientists study how supernova energy dissipates in near-laboratory conditions, like watching ripples spread across a still pond long after the stone has sunk. X-ray observatories have mapped its delicate oxygen and neon filaments, tracing where the blast wave heats interstellar gas to millions of degrees, while radio telescopes detect the faint synchrotron glow of electrons spiraling through its magnetic fields. These observations reveal something unexpected. Even in this advanced age, the remnant shocks haven't slowed as much as models predict, hinting that the interstellar medium in this galactic neighborhood might be far less dense than we assume. But G65, 3 plus 5, 7's real gift is its chemical transparency. Without the glare of brighter remnants, astronomers can isolate elements like sulfur and argon in its debris with unusual clarity, heavy atoms forged in the progenitor star's final moments and scattered by the explosion. The distribution of these elements doesn't match standard supernova models, suggesting the dying star might have undergone peculiar nuclear burning phases or unusual mass loss before its demise. It's a reminder that faint doesn't mean insignificant. Sometimes, the universe's quietest corners hold the most revealing clues. What makes this remnant truly humbling is its role as a cosmic counterpoint. While Cassiopeia A and the Crab Nebula dazzle with their energy, G65, 3 plus 5, 7 demonstrates how supernova age gracefully, their fury fading into a slow, purposeful redistribution of matter and energy. Its filaments, though faint, are weaving freshly forged elements back into the galaxy's tapestry, elements destined for future stars, planets, and perhaps even life. And as we refine our tools to study such subtle structures, we're learning that the cosmos speaks as meaningfully in whispers as it does in shouts. Now, imagine remnants where silence gives way to invisible forces, where magnetism doesn't just shape stellar debris, but twists it into configurations that defy intuition. These are the cosmic laboratories where the universe's hidden frameworks reveal themselves, not through light, but through the dance of particles and fields we're only beginning to decode. G54, 1 plus 0, 3 isn't just a stellar graveyard, it's a cosmic power plant where a neutron star's relentless energy transforms destruction into dazzling light. At the heart of this remnant, a pulsar spins 7 times per second, whipping particles into a frenzy and sculpting a luminous wind nebula that glows across the electromagnetic spectrum. Unlike the fading embers of older remnants, this system crackles with activity, its pulsar channeling energy so efficiently that the surrounding gas fluoresces like a celestial neon sign. What makes G54, 1 plus 0, 3 special isn't just its beauty, it's the textbook example of how neutron stars become long-term custodians of their own debris. The dynamics here read like a physics experiment scaled to interstellar proportions. As the pulsar's magnetic field accelerates electrons to near light speed, they spiral along field lines, emitting synchrotron radiation that paints the nebula in vivid X-rays and radio waves. This isn't random chaos. The nebula's intricate ring-like structure reveals how the pulsar's wind collides with slower-moving supernova debris, creating shock fronts that heat and illuminate the surrounding material. It's a delicate balance. The pulsar's energy must be powerful enough to light up the remnant, yet not so violent that it blows the debris apart entirely. By studying this equilibrium, astronomers gain clues about how pulsar winds inject energy into galaxies over millennia, subtly shaping star-forming regions long after their parent explosions fade. But G54, 1 plus 0, 3 holds deeper secrets. Spectroscopy of its nebula shows unexpected concentrations of silicon and argon, elements typically forged deep within massive stars and scattered by supernova. Their presence here, mingling with the pulsar's high-energy glow, suggests the original explosion may have been unusually efficient at mixing the star's layered interior. Meanwhile, the pulsar itself defies expectations. Its spin-down rate, the gradual slowing of its rotation, hints at a magnetic field stronger than most models predict, possibly due to exotic matter in its core. This remnant's greatest lesson might be about cosmic legacy. While the supernova that birthed it lasted mere weeks, the pulsar's influence will persist for millions of years, its wind nebula acting as a sustained beacon of high-energy physics. It's a reminder that stellar deaths aren't singular events, but cascades of consequences where a single explosion can ignite processes that outlive civilizations, galaxies, even species. As we turn our gaze to remnants where time stretches even farther, we'll encounter explosions so ancient their light has vanished, leaving only whispers in the form of warped magnetic fields or ghostly gamma-ray echoes, testaments to how the universe remembers what our eyes cannot see. G350, 10, 3 isn't playing by the rules. This jagged, lopsided remnant looks like a stellar explosion frozen mid-tantrum. Unlike the graceful shells of most young supernova remnants, this one sprawls across the constellation Scorpius like a cosmic ink blot, its debris flung wildly to one side while the other appears almost crimped inward. The asymmetry is so extreme that astronomers initially struggled to identify it as a supernova remnant at all, mistaking its bizarre shape for a collision between unrelated gas clouds. But this isn't chaos for chaos' sake. Every kink and gap in G350, 10, structure whispers secrets about how some stars die in spectacularly unbalanced fashion. What makes this remnant especially valuable is its youth. Estimated at just 600 to 900 years old, it's a celestial newborn compared to relics like the Crab Nebula, offering a rare snapshot of a supernova's immediate aftermath. X-ray telescopes reveal its shockwaves plowing into surrounding gas at over 4,000 kilometers per second, heating material to millions of degrees and lighting up like a fireworks finale. But the real fascination lies in what's missing. No central neutron star pulses detectably within the debris. Either the core collapsed into an unusually quiet black hole, or the explosion's violence kicked the stellar corpse clear out of the remnant entirely, sending it careening through interstellar space like a cosmic fugitive. The leading theory for G350, 10, odd shape involves a dramatic last act. Imagine a massive star that shed most of its outer layers before exploding, leaving behind a lopsided envelope of gas. When the supernova detonated, the blast encountered far less resistance on one side, allowing debris to surge outward unimpeded while the other side collided with denser material, crumpling inward. It's like setting off a firework inside a cardboard box. With one wall missing, the explosion expands freely in one direction, while the remaining walls contain it. This scenario challenges textbook models of spherical explosions, proving that stellar deaths can be as unique as the stars themselves. Yet G350, 103's greatest contribution might be what it reveals about cosmic diversity. By studying its irregularities, astronomers recalibrate their understanding of how supernovae inject energy and heavy elements into galaxies. Not all explosions distribute their bounty evenly. Some, like this one, might scatter precious metals in concentrated jets, creating pockets of enriched material that could influence star formation for millennia. And as we turn our gaze to remnants where energy reaches even more extreme extremes, we'll encounter explosions so powerful they don't just light up the cosmos, they rewrite the laws of physics in their wake. Buried within the constellation Sagittarius lies a cosmic time capsule, G11-20-3, a supernova remnant that bridges ancient stargazing with cutting-edge astrophysics. This compact, shell-like structure, barely 20 light-years across, pulses with secrets from an explosion that may have lit up Earth's skies over 16 centuries ago. Chinese court astronomers in the year 386 recorded a guest star glowing for months near the modern constellation Scorpius, a celestial event now believed to match this very remnant. What makes G11-20-3 extraordinary isn't just its historical pedigree, but how its young pulsar spinning 15 times per second offers a rare chance to study a neutron star's early life stages, frozen in time like a stellar toddler caught mid-tantrum. X-ray observations reveal why this remnant stands out. Unlike the sprawling chaos of Cassiopeia A or the delicate filaments of the Veil Nebula, G11-20-3's debris forms an almost perfect sphere, its symmetry suggesting the progenitor star exploded with unusual uniformity. At its heart, the pulsar's fierce winds collide with surrounding debris, creating shock fronts that glow like a cosmic halo. But here's the twist: the pulsar isn't centered. This slight offset hints that the explosion may have given the neutron star a gentle kick, a clue that even spherical supernova might harbor hidden asymmetries. Connecting this remnant to the 386 event required cosmic detective work. By measuring its expansion rate and tracing the pulsar's motion backward, astronomers narrowed the explosion's timeline to within a few centuries of the ancient sighting. Supporting evidence came from light echoes, faint reflections of the original blast bouncing off interstellar dust, that matched the expected brightness of a supernova visible to the naked eye. It's as if the universe left breadcrumbs across 1,600 years, allowing us to piece together a stellar death from fragments of light and historical scrolls. Beyond its historical allure, G11-20-3 serves as a natural particle accelerator. The pulsar's magnetic field whips electrons to near light speed, generating gamma rays that help unravel how supernovae contribute to the cosmic rays constantly raining down on Earth. These high-energy particles, some carrying millions of times more energy than anything produced in human colliders, may owe their origins to environments exactly like this, where the turbulent aftermath of stellar death becomes a factory for interstellar radiation. Yet G11-20-3's greatest gift might be its rarity. Few remnants this young retain such clear links to human records, offering a benchmark for how neutron stars evolve in their first millennia. As we turn to even more energetic remnants, we'll encounter explosions where the birth of cosmic rays isn't just a side effect. It's the main event, with shockwaves so powerful they can fling atomic nuclei across galactic distances. These cosmic power plants don't just illuminate the past, they shape the invisible forces threading the universe. Tucked away in the galactic plane, G15, 9+0, 2 eluded detection for centuries, a cosmic sleeper agent among supernova remnants until X-ray telescopes finally exposed its hidden brilliance in 2005. This celestial latecomer to our catalogs isn't just another debris field, it's a chameleon-like hybrid, blending characteristics of both shell type and composite remnants with an elegance that's forcing astronomers to rethink their classification systems. Its sprawling filaments glow with the telltale signatures of shock-heated iron and silicon, while the absence of a clear central pulsar poses a tantalizing riddle. Did the progenitor star collapse into a black hole, or is its neutron star simply shrouded in dust too thick for our instruments to penetrate? What makes this remnant particularly captivating is its youth. Estimates suggest the explosion occurred a mere 2,000 to 4,000 years ago, making it one of the Milky Way's freshest supernova in cosmic terms. Yet despite its recent origin, G15, 9+0, 2 hides in plain sight, obscured by the dense interstellar gas of the galactic midplane. This stealthy nature hints at an entire population of overlooked remnants waiting to be discovered, their faint emissions drowned out by the galaxy's luminous backdrop. Advanced radio surveys have since peeled back the veil, revealing intricate substructures where the blast wave interacts with molecular clouds, creating luminous knots that flicker like candles in a fog. The real revelation lies in G15, 9+0, 2's dual personality. Western regions display the crisp, spherical shock fronts typical of young remnants, while the eastern sector dissolves into frayed tendrils, evidence that the explosion encountered pre-existing cavities carved by the progenitor star's stellar winds. This striking asymmetry serves as a three-dimensional textbook, illustrating how a star's life shapes its death. Spectroscopic studies have even detected trace elements like chromium and titanium in its debris, metals typically forged in the innermost layers of supernova, now flung far into space by the explosion's uneven forces. Yet beyond its scientific value, this remnant carries a profound symbolic weight. Its late discovery underscores how much of our own galaxy remains uncharted, a humbling reminder that the cosmos reserves its greatest surprises for those patient enough to look deeper. As we shift our gaze from these hidden gems to remnants where order emerges from chaos, we'll encounter cosmic structures so geometrically perfect, they seem to whisper of universal patterns woven into the fabric of reality itself. G18, 95-1, one doesn't just expand into space, it claws its way through the cosmos, its shock fronts twisted into jagged tendrils that resemble frosted glass shattering in slow motion. This remnant's chaotic beauty isn't random, it's a fossilized record of a supernova colliding with a galactic obstacle course, where dense clouds of interstellar gas acted like cosmic speed bumps, warping the explosion's aftermath into intricate knots and filaments. Unlike the crisp, symmetrical shells of younger remnants, G18, 95-1, one's fragmented structure tells a story of resistance, of a star's dying fury meeting the uneven terrain of the galaxy head-on. What makes this remnant so valuable to astronomers isn't just its complexity, but what that complexity reveals about the invisible landscape of the interstellar medium. Radio telescopes trace the faintest tendrils of G18, 95-1, one's debris, mapping where shockwaves plowed into pockets of cold molecular hydrogen, while X-ray observations spotlight regions where gas heats to millions of degrees as it rams against denser material. These collisions create a mosaic of temperatures and densities, offering a real-time lab for studying how energy dissipates across cosmic environments. The remnants' faintest filaments may even hold clues to an older mystery: cosmic rays, those high-energy particles bombarding Earth from deep space, which could gain their incredible speeds in these turbulent shock fronts. But G18 95-1's greatest surprise lies in its asymmetry. While most supernova remnants fade uniformly, this one blazes brighter along its western edge, where the shockwave appears to have encountered and partially evaporated a previously unseen molecular cloud. The interaction left behind glowing arcs of ionized oxygen and neon, elements typically buried deep within stars, now strewn across space like confetti. Some astronomers speculate the progenitor star might have shaped its own destruction, its stellar winds carving cavities that later funneled the explosion's energy in unpredictable directions. Yet for all its scientific value, this remnant serves as a humbling reminder. The cosmos refuses to conform to tidy models. G18 95-1's tortured geometry proves that stellar deaths aren't isolated events, but conversations between stars and their environments, where a single explosion's legacy hinges on the gas, dust, and magnetic fields it encounters. As we turn our gaze to remnants where particle acceleration reaches even more extreme extremes, we'll find explosions that don't just light up the sky, but act as natural supercolliders, hurling atoms across the galaxy with forces no human machine could ever replicate. G21 50-9 glows like a cosmic bullseye, a supernova remnant where practically all the action happens at its brilliant core. Unlike most remnants that dazzle with intricate filaments or sprawling shock fronts, this compact structure in the constellation Scutum shines brightest at its heart, where an unseen powerhouse, likely a rapidly spinning neutron star, pumps relentless energy into its surroundings. The result: a luminous X-ray halo that pulses with the rhythm of particle acceleration on an astronomical scale, making this unassuming debris field one of the galaxy's most efficient natural laboratories for studying how stars turn destruction into light. What sets G21 50-9 apart isn't just its radiant center, but the precision with which it demonstrates a universal process. The pulsar's furious rotation generates powerful magnetic fields, turning the surrounding nebula into a colossal particle accelerator. Electrons whip along these invisible lines at nearly light speed, emitting synchrotron radiation that glows brightest in X-rays, a telltale signature of extreme physics at work. This isn't just theoretical. Telescopes have mapped the nebula's intricate spectral fingerprints, revealing how energy cascades from the core outward, like ripples from a stone tossed into a pond of charged particles. Yet the real fascination lies in the remnant's paradoxes. Despite its energetic core, G21 50-9 lacks the dramatic outer shock structures seen in younger remnants like Cassiopeia A. One theory suggests the original explosion occurred inside a pre-existing bubble of low-density gas, perhaps carved by the progenitor star's stellar winds, allowing the debris to expand freely without forming crisp outer shells. Alternatively, the pulsar's wind might have overpowered the remnant's expansion early on, funneling most of the energy inward rather than letting it dissipate into space. Either way, this lopsided energy distribution offers a masterclass in how environment shapes a supernova's afterlife. But G21 50-9's greatest gift to science might be its role as a cosmic benchmark. By measuring how its X-ray luminosity changes over years, astronomers can test theories about pulsar wind nebulae across the universe systems where the rules of electromagnetism and fluid dynamics collide at energies impossible to replicate on Earth. It's a reminder that sometimes the most profound discoveries come not from the flashiest celestial objects, but from those that serve as steady, reliable guides to the universe's hidden mechanisms. As we peer deeper into the catalog of remnants, we'll encounter explosions where energy doesn't just concentrate at the core, but warps the very fabric of spacetime, where magnetic fields grow so strong they twist light, and temperatures soar to levels unseen since the universe's fiery birth. These extreme environments don't just push the limits of physics, they redefine what we thought was possible in the cosmos. G27, 4 plus 0, 0 is the cosmic equivalent of a puzzle missing half its pieces, a supernova remnant that refuses to conform to any textbook classification. Where most remnants declare their nature through crisp shock fronts or pulsar-powered nebulae, this enigmatic structure in the constellation, Sagittarius, offers only contradictions. Its radio emissions suggest a classic shell-like morphology, yet X-ray observations reveal no clear boundary where debris meets interstellar space, as if the explosion's energy dissipated unevenly into the void. Even more baffling is its spectral fingerprint. Traces of ionized sulfur and argon glow where astronomers expect to see oxygen, hinting at nucleosynthesis processes that stray from standard stellar death scenarios. This celestial outlier forces scientists to confront the limits of their categorization systems. Traditional supernova taxonomy splits remnants into clear types, shells, composites, filled centers, but G27, 4 plus 0, 0 straddles multiple categories while fully belonging to none. Some researchers propose it represents a rare, mixed morphology remnant, where a supernova detonated near a dense molecular cloud, distorting the debris field. Others speculate it might showcase an entirely new class of explosion, perhaps from a progenitor star with unusual rotation or magnetic fields that twisted the detonation's symmetry. The ambiguity isn't just academic, it underscores how much we still don't know about the diversity of stellar deaths. What makes G27, 4 plus 0, 0 particularly valuable is how it mirrors discoveries in other galactic neighborhoods. Similar unclassifiable remnants have been spotted in the Large Magellanic Cloud and Andromeda, suggesting these oddballs aren't flukes but integral pieces of the cosmic puzzle. Their existence hints that our current classification frameworks might be too rigid, like trying to sort a spectrum of colors into just 3 boxes. Every observation of this rebellious remnant chips away at old assumptions, revealing subtleties, like faint radio filaments aligning with local magnetic fields or infrared bright dust pockets, that could rewrite how we model supernova mechanics. Yet for all its mystery, G27, 4 plus 0, 0 offers a profound lesson. The universe thrives on exceptions. Just when we think we've mapped the boundaries of stellar behavior, remnants like this emerge to remind us that nature's creativity outstrips human imagination. And as we peer deeper into the catalog of cosmic aftermaths, we'll encounter explosions that don't just defy classification. They illuminate the invisible frameworks of the universe itself, from dark matter's pull to the magnetic webs stitching galaxies together. These aren't merely stellar graveyards, they're portals to physics we've yet to name. G29, 703 isn't just another supernova remnant, it's a cosmic detective story with a tantalizing twist. At its heart, hidden within swirling debris, lurks an object so enigmatic that astronomers still debate its true nature. Most remnants proudly display their neutron stars or black holes, but this one keeps its secrets close, emitting faint, erratic signals that defy easy classification. Some theories suggest we're seeing a neutron star cloaked in ultra-dense matter, its magnetic field tangled beyond recognition. Others propose something rarer, a quark star, where crushing pressures have smashed atomic particles into exotic states that rewrite the rules of physics. What makes this central object so perplexing is its radio silence. Unlike the rhythmic pulses of typical pulsars, G2970-3's core flickers unpredictably, as if struggling to be heard through a cosmic fog. X-ray telescopes catch brief flares, hints of activity beneath the surface, while infrared observations reveal a halo of heated dust, possible evidence of a magnetar's intense magnetic field cooking surrounding material. It's as if the remnant can't decide what kind of stellar corpse it hosts, leaving astronomers to piece together clues from scattered emissions, yet this ambiguity is precisely what makes G2970-3 invaluable. By studying its quirks, scientists probe the boundary between neutron stars and black holes, the elusive mass range where collapsing stars might become one or the other. The remnant's chemical fingerprints add another layer. Its debris shows unusual concentrations of titanium and chromium, metals forged under conditions so extreme they challenge our models of supernova nucleosynthesis. Every irregularity in this system forces us to reconsider how matter behaves when crushed beyond earthly limits. Beyond its scientific intrigue, G2970-3 serves as a humbling reminder. Even with advanced telescopes, some stellar remnants refuse to surrender their mysteries easily. They guard their truths behind veils of dust, magnetic chaos, or sheer distance, teaching us patience as we slowly decode their stories. And as we turn from these hidden compact objects to remnants where magnetism takes center stage, we'll encounter explosions that don't just leave behind debris. They sculpt the cosmos with invisible forces powerful enough to bend light itself. G31-9+0 isn't just another supernova remnant. It's a cosmic chemist's dream, a swirling laboratory where the universe's elemental recipes are written in light. Imagine a star so massive it fused atoms in its core like a celestial pressure cooker, then detonated with such violence that it scattered its chemical experiments across space. That's the story hidden in this remnant spectrum, where X-ray and radio telescopes reveal a dazzling array of elements, not just the usual hydrogen and helium, but surprising concentrations of neon, argon, and even traces of titanium. These aren't random ingredients, they're the telltale signatures of a progenitor star that burned hotter, fused heavier, and died more spectacularly than most. What makes this chemical mix so revealing is how it maps to specific fusion processes. The overabundance of neon, for example, suggests the star's core reached temperatures where carbon atoms could collide and merge, a phase only the most massive stars experience before collapse. Meanwhile, the unexpected pockets of titanium hint at explosive nucleosynthesis, where shockwaves from the supernova itself forged rare isotopes in white-hot instants. It's as if we're sifting through the ashes of a cosmic alchemist's workshop, finding vials of elements that shouldn't exist side by side under normal stellar conditions. But G31-9+0's greatest gift might be its challenge to stellar timelines. Most models predict these heavy elements form gradually over a star's lifetime, yet here they're mingled in ways that suggest abrupt, chaotic synthesis, like a chef throwing all the ingredients into the pot at once. Some theorists speculate this points to a hypernova, an even more energetic variant of a supernova, where the dying star's rotation or magnetic fields turbocharged its final explosion. Others wonder if the progenitor was part of a binary system, its chemistry altered by a companion star's gravitational tugs before catastrophe struck. As we decode these elemental hieroglyphs, we're also glimpsing the origins of everything around us. The same titanium atoms glowing faintly in this remnant might one day end up in spacecraft hulls or medical implants, while its scattered neon could illuminate future cities. G31, 9 plus 0, 0 reminds us that supernovae aren't just endings, they're dispersal events, spraying the raw materials of technology, art, and even life itself into the void. Yet for all its revelations, this remnant is just one page in a much longer story. Beyond it lie explosions that warp our perception of time itself, where light echoes from supernova flash like cosmic Morse code across millennia, and remnants so ancient they've become interwoven with the galaxy's spiral arms. These time-bending relics don't just illuminate the past, they force us to rethink how destruction and creation dance across the eons. G34, 70, 4 isn't just a supernova remnant, it's a cosmic wrecking ball smashing through a labyrinth of interstellar clouds, each collision sculpting its debris into a luminous masterpiece of shock physics. Picture a star's death throes reverberating through space, its shockwaves plowing into not one, but multiple dense gas clouds at velocities topping 8,000 kilometers per second. Where these waves meet resistance, the interstellar material lights up in brilliant X-rays, glowing filaments of oxygen, and neon twisted into surreal shapes by forces strong enough to tear atoms apart. This isn't chaos. It's a high-energy laboratory where astronomers witness real-time chemistry lessons written across light years. What makes G34, 70, 4 so pivotal is how clearly it demonstrates supernova's role as galactic landscapers. Each collision zone acts like a cosmic blender, churning heavy elements forged in the explosion iron, silicon, sulfur into the colder, primordial gas of the clouds. Infrared telescopes reveal where these shock fronts compress pockets of molecular hydrogen, jump-starting chemical reactions that might one day form complex organic molecules. It's a violent form of cosmic recycling. The same explosion that obliterated a star now seeds the raw materials for future stellar nurseries, planets, or even the building blocks of life. But the real magic lies in the remnants' asymmetry. Unlike uniform shells like the Cygnus loop, G34, 70, 4's debris forms jagged tendrils, some surging ahead where the path was clear, others stalled where dense clouds stood firm. This patchwork expansion offers a 3D map of the interstellar medium's hidden structure, exposing densities and magnetic fields that would otherwise remain invisible. Radio observations even detect synchrotron radiation flickering along shock fronts, evidence of electrons accelerated to near light speed, a preview of how supernovae generate the cosmic rays that constantly bombard our solar system. Yet G34, 70, 4's greatest lesson might be about scale. While we see its shockwaves lighting up local clouds, simulations suggest its energy could reverberate through the galaxy for millennia, subtly influencing star formation rates and chemical distributions far beyond its visible boundaries. It's a reminder that stellar deaths aren't isolated events, but catalysts in an endless cycle where destruction and creation orbit one another like cosmic partners. Now, imagine remnants where these interactions reach even more extreme energies, where shockwaves don't just reshape gas clouds, but unleash forces powerful enough to warp spacetime itself. These are the universe's ultimate particle accelerators, where the rules of physics get rewritten in the white-hot afterglow of stellar catastrophe. G39-20-3 doesn't just fade into the cosmic background, it announces its presence with a dramatic double shockwave, as if the star couldn't decide how to die and left behind two distinct signatures of its destruction. The inner shock front races outward at thousands of kilometers per second, glowing fiercely in X-rays where it heats debris to millions of degrees. Surrounding it, a second, larger shock plows into the interstellar medium like a snowplow through fresh powder, creating a luminous halo of compressed gas. This layered structure isn't just for show, it's a fossilized record of the supernova's energy dissipating in stages, offering astronomers a rare chance to study how explosions evolve over time. What makes this remnant so valuable is what the twin shocks reveal about the star's final moments. The inner front likely marks where the explosion's initial energy slammed into material shed by the progenitor star shortly before its death, a cosmic pre-explosion farewell. The outer shock, meanwhile, shows how that energy interacts with the undisturbed interstellar medium. By comparing their velocities and temperatures, scientists can reconstruct the explosion's power curve, almost like rewinding a stellar detonation frame by frame. Some theories suggest the double structure hints at a delayed detonation, where the star's core collapsed unevenly, releasing energy in pulses rather than a single blast. But G39-20-3's surprises don't end there. Radio telescopes detect strange wisps of synchrotron radiation weaving between the shock's telltale evidence of electrons being accelerated to near light speed. These high-energy particles aren't just cosmic graffiti, they're prototypes for the mysterious cosmic rays that constantly rain down on Earth. The remnants' nested shocks act like natural particle colliders, with magnetic fields between the two fronts channeling electrons in spiraling paths until they're flung into space like bullets from a rifle. It's a vivid demonstration of how supernova, once thought to be purely destructive, actually engineer the universe's most energetic particles, yet the real magic lies in the questions G39-20-3 leaves unanswered. Why do some remnants develop this dual structure while others explode uniformly? Could binary star systems or exotic magnetic fields explain the phenomenon? Every observation peels back another layer of complexity, proving that even well-studied supernova still guard secrets. And as we shift our gaze to remnants where particle acceleration reaches even more extreme extremes, we'll encounter explosions so powerful they don't just create cosmic rays, they launch them across galaxies with forces that dwarf anything in our solar system. G41-10-3 defies the cosmic chaos you'd expect from a stellar explosion. Instead of tangled magnetic fields and jumbled debris, this remnant glows with an almost mathematical precision, its magnetic lines aligned like iron filings around a perfectly symmetrical magnet. While most supernova remnants resemble splattered paint across the interstellar canvas, this one stands apart as a masterpiece of cosmic order, its magnetic architecture so uniform it could pass for an artificial construct. The secret behind this eerie organization might lie in the progenitor star's final moments. Imagine a massive star spinning rapidly before its collapse, its rotation imprinting structure onto its magnetic field like a potter's hands shaping clay. When the supernova detonated, that ordered magnetism may have been preserved, or even amplified, by the explosion's shockwaves, creating the remnant's uncannily tidy magnetic scaffolding. Alternatively, the the blast might have expanded into an unusually smooth pocket of interstellar space, undisturbed by dense clouds or turbulent gas that typically warp a remnant's magnetic geometry into chaos. What makes G41.10.3 invaluable to astronomers isn't just its beauty, it's the way this magnetic order acts as a natural laboratory. Charged particles spiral along those disciplined field lines, emitting synchrotron radiation that reveals how energy flows in environments where magnetism dominates over turbulence. These conditions mimic those found in far more extreme cosmic settings, like the jets of active galaxies, but here, they're close enough to study in exquisite detail. Even the remnants' radio emissions tell a story of control. Unlike the crackling static of most remnants, G41.10.3 signal is a steady hum, as if the entire structure vibrates in harmony. Yet for all its symmetry, this remnant whispers tantalizing contradictions. X-ray observations reveal faint, wispy filaments that refuse to follow the magnetic grid, hints that even here, pockets of rebellion linger. Some researchers speculate these outliers might trace the paths of ancient stellar winds, ejected by the progenitor star long before its demise, now glowing as ghostly reminders of its turbulent past. Others suggest they could be scars from a companion star, torn apart in the explosion and leaving behind magnetic disturbances like footprints in wet sand. G41.10.3's greatest lesson might be about cosmic balance. Its existence proves that even amid the universe's most violent events, pockets of order can emerge, not through simplification, but through the precise alignment of unimaginable forces. As we turn our gaze to remnants where symmetry takes even more breathtaking forms, we'll encounter explosions that don't just reflect hidden patterns in nature, but illuminate the fundamental rules shaping reality itself. G43.30.2 isn't just a supernova remnant, it's a cosmic clock that can't decide what time it's keeping. By all outward appearances, this expanding cloud of debris should be a sprightly young remnant, its shockwaves racing through space at speeds suggesting an explosion no more than a few thousand years ago. Yet when astronomers examine other telltale signs like the cooling rate of its neutron star or the chemical mixing of its filaments, they get a radically different reading. This stellar ghost might actually be tens of thousands of years old. It's as if the universe handed scientists a stopwatch and an hourglass, then grinned as they spat out contradictory answers. The key to this chronological conundrum lies in the remnant's environment. Unlike most supernovae that explode into uniform interstellar space, G43.30.2 shock fronts are plowing through a bizarre patchwork of dense clouds and near-vacuum tunnels, some carved by the progenitor star's own stellar winds long before its demise. Where the debris encounters resistance, it slows dramatically, mimicking the sedate expansion of an ancient remnant. But in neighboring regions where the path is clear, shockwaves surge ahead at velocities typical of much younger explosions. This cosmic obstacle course creates an optical illusion on galactic scales, forcing astronomers to rethink how they date stellar cataclysms when the surrounding medium isn't playing fair. What makes G43.30.2 invaluable isn't just the puzzle itself, it's the forensic tools scientists develop to solve it. By mapping the remnant's turbulence with radio telescopes and comparing X-ray emissions across different sectors, researchers can essentially correct for environmental factors, refining models that date supernova across the galaxy. Some teams have even proposed using the remnant's neutron star as a calibration point, measuring how its spin rate and surface temperature diverge from predictions based solely on expansion speed. These discrepancies become Rosetta Stones, helping decode the hidden histories of older, fainter remnants where only fragmentary clues remain. Yet beyond chronology, this celestial contradiction holds deeper implications. The same uneven terrain distorting G43.302's age estimates also acts as a natural particle accelerator, with shock fronts ramming into gas clouds at different angles and energies. These collisions generate cosmic rays with a far wider energy spread than uniform remnants, produce proof that environment doesn't just alter how we perceive stellar deaths, but how those deaths actively reshape the cosmos. As we turn our gaze to remnants where particle acceleration reaches even more extreme extremes, we'll encounter explosions that don't merely challenge our models, they rewrite the rules of galactic physics altogether. G46.803 isn't just another supernova remnant, it's a cosmic rule-breaker, broadcasting radio waves in patterns that defy every textbook model. While most remnants emit synchrotron radiation in predictable spirals, as electrons spiral along magnetic fields, this enigmatic structure in the constellation, Aquila, crackles with irregular bursts and strange spectral kinks, as if some unseen force is rewriting the rulebook on particle acceleration. The anomalies aren't just academic curiosities, they're clues pointing to exotic physics at play, where shockwaves might be interacting with rogue interstellar clouds or tangled magnetic fields in ways we've never witnessed before. What makes G46.803 truly fascinating is how its radio contradictions manifest. In some regions, emissions intensify abruptly, like a cosmic volume knob being cranked to maximum, while other zones fall eerily silent despite perfect conditions for radiation. One theory suggests the remnant's progenitor star might have exploded near a dense cluster of magnetized filaments, celestial power lines that now focus and amplify particle beams in chaotic, unpredictable ways. Alternatively, the supernova's shock fronts could be ricocheting off previously unknown pockets of ultra-dense gas, creating turbulent eddies where particles gain energy through bizarre, non-linear processes. Yet the real value of this radio rebel lies in its power to push astrophysics forward. Every irregular pulse challenges conventional theories about how cosmic rays, those high-energy particles zipping through space, get their incredible speeds. Normally, astronomers attribute their acceleration to orderly shockwave dynamics, but G46.803's messy emissions hint at wilder mechanisms, perhaps involving magnetic reconnection or plasma instabilities usually seen near black holes. It's as if the universe tucked a laboratory for extreme physics inside this unassuming remnant, daring us to decode its secrets, and the implications stretch far beyond this single object. If G46.803's anomalies reflect broader, overlooked phenomena, they could explain why some cosmic rays hit Earth with energies that dwarf anything human colliders can produce. The remnant's radio whispers might be tracing the invisible highways these particles travel, paths forged in supernova, where the rules bend, and the universe's most energetic forces run unchecked. But G46.803 is just the beginning. Beyond it lie remnants where conditions grow even more extreme, where magnetic fields twist spacetime itself, and temperatures soar beyond comprehension. These are the cosmos' ultimate proving grounds, where the laws of physics are stretched to their limits, and every explosion writes its own defiant chapter in the story of the universe. G49.207 doesn't just challenge our expectations, it shatters them. While most supernova remnants proudly display a neutron star at their core, This enigmatic structure in the constellation Aquila whispers a far more intriguing possibility: a lurking black hole, its presence betrayed only by the absence of expected pulsations and the peculiar motions of surrounding gas. If confirmed, this cosmic phantom would join an elite club of remnants hiding stellar mass black holes, objects so elusive that astronomers have catalogued fewer than a dozen candidates across the entire Milky Way. What makes this remnant so compelling isn't just the potential black hole, it's the forensic evidence pointing to its existence. X-ray telescopes detect a compact, ultra-bright source at G49.20.7's heart, glowing with the telltale signature of matter spiraling into an intense gravitational field. Yet unlike neutron stars, which often flicker with precise radio pulses, this object remains eerily silent, its emissions steady as a drumbeat. Even more telling, the remnant's debris shows unusual asymmetries. Some filaments race outward faster than others, as if the explosion's energy was funneled unevenly, perhaps by a black hole's disruptive influence during the star's collapse. The rarity of such systems forces us to rethink stellar life cycles. Conventional wisdom suggests only the most massive stars collapse directly into black holes, while lighter ones leave behind neutron stars. But G49.20.7's progenitor appears to have danced on the edge of these categories, massive enough to birth a black hole, yet not so heavy that its explosion would completely obliterate the surrounding remnant. This cosmic tightrope walk offers clues about the mass gap between neutron stars and black holes, a controversial frontier where stellar fates grow unpredictable. Yet the true significance of G49.20.7 lies beyond classification. Its existence hints at hidden diversity in supernova mechanics, explosions where magnetic fields, rotation, or even companion stars might tip the balance between creating a neutron star or a black hole. Every subtle detail in its debris, the distribution of iron, the velocity of shock fronts, adds another piece to this puzzle, helping astronomers refine models that predict how stars transform in their final moments. As we step back to view these remnants collectively, a profound pattern emerges. From pulsar-powered nebulae to black hole hideouts, each supernova carves its own path through cosmic history, scattering heavy elements, accelerating particles, and occasionally leaving behind compact objects that push physics to its limits. Together, they form a galactic feedback loop, where the deaths of stars shape the births of new ones, weaving an intricate tapestry of creation and destruction across the eons. And as our tools grow sharper, who knows what other exceptions to the rules await discovery, each one a reminder that the universe thrives on surprise. These radiant remnants are far more than celestial graveyards. They are the universe's great recyclers, transforming destruction into creation on a cosmic scale. Every element heavier than iron in your body, from the calcium in your bones to the zinc in your enzymes, was forged in the heart of a dying star and scattered across space by explosions like these. The shockwaves rippling through remnants like Cassiopeia A and the Veil Nebula act as interstellar plows, churning up clouds of gas and dust until gravity takes over, collapsing them into new stellar nurseries. It's an astonishing cycle where the death of one star becomes the raw material for thousands more, complete with fresh planetary systems that might one day harbor life. What makes this process truly remarkable is the precision hidden within the chaos. Supernova remnants don't just spew elements randomly, they distribute them in patterns that mirror the progenitor star's layered interior. When telescopes analyze remnants like G292.0+1.8, They find distinct zones rich in oxygen, neon, and silicon, like peeling back the pages of a stellar autobiography, where each chapter reveals what elements were fused at different depths before the explosion. These chemical fingerprints allow astronomers to reconstruct the life story of stars that died before humans walked the Earth, tracing how their internal fusion processes evolved over millennia. Beyond chemistry, remnants serve as natural laboratories for physics we could never replicate on Earth. The turbulent shock fronts of objects like Tycho's supernova accelerate particles to velocities approaching light speed, creating cosmic rays that continually bombard our planet. Some of these high-energy particles carry millions of times more energy than anything produced in human particle colliders, and we're only beginning to understand how remnants manufacture them. The intricate dance between magnetic fields and charged particles within remnants like the Crab Nebula offers clues to this process, showing how nature builds accelerators on scales dwarfing human engineering. Perhaps most profoundly, studying these 46 remnants reveals how interconnected the cosmos truly is. The same explosion that lights up a galaxy for weeks also seeds it with the ingredients for rocky planets, organic molecules, and even the potential for life. When we map how remnants like W44 interact with molecular clouds, we're witnessing the universe's grand recycling program in action, where generations of stars pass their elemental legacy forward. This perspective shifts how we see our own place in space. The iron in our blood, the gold in our jewelry, even the silicon in our smartphones all originated in stellar explosions long before our solar system formed. What ties these remnants together isn't just their explosive origins, but their role as architects of cosmic change, from sculpting vast bubbles in the interstellar medium to triggering waves of star formation. Their influence stretches far beyond their visible boundaries. As our instruments grow more sensitive, we're finding even fainter echoes of ancient supernova woven into the galaxy's fabric, proof that these events don't just shape space, but time itself, with repercussions echoing across billions of years. The next time you gaze at the night sky, remember, you're not just seeing points of light, but the aftermath of cosmic rebirths that continue to reshape the universe around us. From the intricate filaments of the Crab Nebula to the enigmatic silence at the heart of G49, 207, these 46 remnants aren't just scattered debris, they are the universe's way of turning catastrophe into artistry. Every swirling tendril of gas, every shockwave rippling through space, carries the signature of a star's final act, a masterpiece painted in elements forged under unfathomable pressure and heat. But here's the breathtaking truth: these explosions aren't in points. They're cosmic catalysts, scattering stardust that will one day coalesce into new worlds, new stars, even the building blocks of life itself. Take a single breath, and you're inhaling oxygen atoms that likely passed through a supernova's fury billions of years ago. The gold in a wedding ring, the silicon in a smartphone screen, these are the recycled gifts of stellar deaths that occurred long before Earth formed. Remnants like Cassiopeia A and the Veil Nebula are more than celestial landmarks. They're active workshops where the universe hammers raw elements into the ingredients of futures we can barely imagine. And with every advance in technology, from space telescopes to neutrino detectors, we're decoding more of their secrets like archaeologists sifting through the ashes of cosmic history. What's truly humbling is realizing how much remains undiscovered. For every remnant we've mapped in dazzling detail, there are countless others hiding in the Milky Way's dusty spiral arms or lurking in distant galaxies, each with its own story to tell. Some might reveal new types of stellar explosions we've yet to witness. Others could challenge our understanding of physics, with magnetic fields so strong they distort space-time or particles accelerated to energies that defy explanation. The mystery of G49.207's silent core is just one reminder. The universe specializes in surprises, and these luminous echoes are its way of whispering clues to those willing to listen. So the next time you gaze at the night sky, remember you're not just looking at points of light. You're seeing the aftermath of cosmic revolutions, the glow of stellar phoenixes that rose from their own ashes to shape everything around us. And as telescopes grow sharper and probes venture deeper, who knows what other chapters of this grand story will uncover? The universe doesn't just hide its secrets, it broadcasts them in the radiant remnants of stars that dared to die spectacularly, lighting the way for discoveries we've yet to dream of. The journey doesn't end here, it's